would ask him after, depending on how he wants it to go. So, Dr. Chumesi, I would call on you, and the flow of the training is entirely up to you, how you want to go about it. So just give us the feedback, and if there's anything we can do to support you, we are happy to do it because we know that you are giving us your invaluable time and supporting this. Thank you very much.
All right. Thank you. Please, can you hear me?
Yes, please.
Yes, we can hear you, but it's a bit faint. If you can push it up a little bit.
Can you hear me
Yes,
now?
a lot better, sir. Thank you very much.
Okay. I don't know whether I'm able to also record from my end. Let me see if it works. But you started a recording, isn't it?
Yes, please.
Okay, so maybe after the session, if you could let me have the recording,
All right.
that would be
All
great.
right, please.
Okay, so I will share my screen and briefly take us through. Okay. So can you see my desktop, please?
Yes, please.
Yes, please, sir, we can say it.
Okay, that's fine. All right. Thank you very much once again for this opportunity to always share with students and other researchers. I'm very humble. Okay, so today, before we go on to today's class, I'll quickly touch a bit on some platforms and other information I think you should know. So first of all, there's a YouTube channel that I already have that is on advanced data analysis in R. So once you get this particular script, or you can just go online and just search with my name. So once you search Clement Chumesi on YouTube, you get access. So on the channel you find access to range of videos already on the channel. So from learning how to program R from scratch up to, I mean, the most important things you need to know in statistics, and most of the let me say tutorials that sometimes I do in Oxford, I even upload them on my YouTube channel. Yeah, so it means that it has range of and then all the previous meetings that I've done with NUGS-CHINA and other student unions are on the channel. So it means that once you go there, you'll be able to learn at your own pace. So at the end of the day, so after today's class, I would also try and upload it there so that you can learn at your own pace. Yeah. So, and there's a platform called Piazza that I use to manage um, the, the programming codes and everything. So this is to say that once you are watching the YouTube channel, all the programming codes you see, including today's lesson, you'll be able to access it on that platform called it's a platform called Piazza. It allows us to be able to, so for instance, all the previous material. So for instance, NUGS-CHINA Masterclass 2022, everything that was used can be found there, for instance. Yeah. So it means that by the end of today's session, I would also upload all the relevant materials we use for today on the Piazza. But in order to be able to access the Piazza platform, you will need to send, first of all, your email address to me to sign up. Yeah. So, and then if you want to send your email address to me, I think if I click on this, so my email is, so you could either use any of them. So that's my Oxford email address, and the next one is my Gmail. Yeah. So it means that once you just go to Google and you type my name, so for instance, if you just go to Google and you type my name, just a minute, you'll be able to find my Oxford account. So you just click on that, and then you'll be able to access any of my emails. Yeah. So just send me an email that you want to enroll on the Piazza platform. That will help you to be able to have full access to all the programming stuff you see on the YouTube channel, as well as what you're going to do for today's lesson. Yeah. So that's just a quick one. So what are going to be some of the learning objectives? I must confess that I was pressed with time, so it meant I only started developing the outline and everything for today's class just this morning when I woke up. Yeah, so it was because of other unfortunate circumstances. But apparently, by the end of today's lesson, we are first of all going to learn a bit about some of the advanced or modern statistical methods that you can use for your research. And then we will talk a bit, brief introduction to what statistical programming is all about. How is it different from programming in the context of, let's say, computer science, engineering, and other disciplines. And then we'll talk a bit about the IDEs. IDEs is something called Integrated Development Environment. It's basically a platform that we use to run programming languages or softwares. And so we'll talk a bit about them. And then we'll learn how to import different data structures into R. So it means by the end of this meeting, suppose, let's say, previously you did your analysis in SPSS. You previously did your analysis in SAS. You previously did your analysis in Stata, but now you want to be able to do it in R. What that means is that you can actually import the Stata data, the SPSS data, the SAS data directly into R and perform your analysis. Unfortunately, because I couldn't get enough time to go about the third phase. So the third phase was just to do a practice task based on a medical application. So it means that we're going to now learn, at least apply two or one of the advanced or modern statistical methods that you should be aware of. So we're just going to focus on survival analysis and look at the model which extends the classical survival analysis. So it means that there is something called multi-states. Let me change this. So this is multi-states Markov modeling. Okay, yeah. So we're going to learn something about an extension to the standard survival models, which I'm very sure that many people are not aware of. But time couldn't permit me to wrap up all the course. So I was in the process and I noticed my time was almost up. So briefly, we'll do our best. And then if anything, I'll add relevant links for students to, or for everyone to just proceed from there. Okay, so now without wasting time, we are just going to talk a bit about some of the advanced, let me copy this briefly. Yeah, so we are going to talk a bit about some of the advanced statistical methods out there. So this is just to say that by the end of this particular session, which I'm about to talk about, you should be able to have a fair idea about existing statistical methods and when and how to use it, right? So the first one is called generalized linear models. And unfortunately for you, I've covered most of these methods on the YouTube channel already, just that there are a couple of new ones that I've not touched on. So it means that once you get access to the YouTube channel, you'll be able to learn most of, including power analysis, how to determine the minimum sample size needed to achieve some amount of power for your study and all sort of things. So there are so many materials there. So don't forget to make use of the YouTube channel as well. And please do help with the subscription. Thank you. All right, so the first one is generalized linear models. So now, basically, what are generalized linear models? So if you've heard of regression is situations where we have some predictor, it's some set of predictors, and we want to see how, okay, someone is asking a question. If I visit YouTube. Oh, okay. So someone is asking where to start from if you visit my YouTube channel, since the person is like new. So basically, it depends on what you want. So if you want to learn how to program R or work in R from scratch, then you start with the first video here. So that's why I called it first lesson. And then we have second lesson, third lesson in that fashion. Okay, so it means that is if you want to start from R programming from scratch. And if you want to rather know, because remember that the knowledge of programming is not just about ability to just develop codes. No, you have to understand the statistics itself. So it means the statistics and the statistical programming must complement each other. This is to say that anything you do in a statistical software, whether it's a programming software, whether you are doing it in SPSS, whether you're doing it in Stata, any wrong thing you do, or you're doing it in GraphPad, Python, or whichever, any wrong thing you do, you get an output. So it means that once the mere fact that you got an output from any statistical analysis does not make it right. So this is to say, knowing the right tool for the right job is very important. So so it means that if you start watching any of these videos here, so let's say, okay, so there's a video on introductory statistics session 1. These are all just more of I would say theoretical, but very like simplified so everyone can understand. So this is if you want to now know when to use and how to know the best statistical method to use depending on the kind of data you're working with. Whether your data is cross-sectional, your data is longitudinal. What do we mean by cross-sectional data? What do you mean by longitudinal data? All those kind of things, you'll be able to find them there. And then the type of regression models we have depend on the nature of the outcome variable and so on and so forth. So it meant that if you want to understand the theory bit, you can get that information there just looking at introductory statistics sessions. And then if it's about power analysis, you want to know how to power your study, then there's a whole video, the whole series on power analysis using G-Power software, which is also there. And then if it's about, for instance, even how to use Mendeley and Quillbot, that has nothing to do with statistics. It is also covered there. And then, so for instance, regression modeling and other inferential tests has been covered. The most important information you need to know in statistics. And then now you notice that what I'm using is different from the classical R software you are aware of, right? So I'll explain the difference. But so what I'm using is called Jupyter Notebook. So with the Jupyter Notebook, you can clearly see that I can even insert pictures. I can insert links. I can also produce all my codes in there, all my R codes in there, and all the graphs will come just beneath it. So it means that anything I do, so if I import a data, everything is just beneath it. I don't need to wait. So you notice that in every other software you've been using, most of the time, you have to now save your outputs in a different file, right? But with the help of the Jupyter Notebook, you don't have to do that. And the beauty is that you can download the file as an executable script. The executable script will be similar as if you had done it in RStudio. Okay, so I was going to talk about IDE later on. And so at this stage, I don't expect you to understand what I mean by RStudio or IDE because it's something I was going to talk on. But the beauty is that you can download your script as if you had done it in IDE. If, let's say, especially those who are doing their PhDs or those who have been meeting supervisors, you don't need to be doing your analysis in just RStudio, and then you have to now save your output separately. Or if you are doing it in SPSS or Stata, you produce your graphs, then you copy and paste into Word, and that's all a bit stressful. And at the end of the day, you might even forget which line of code produced a particular output. So with the help of this, and I can also download it as an HTML file. So if I download it as an HTML file, what that means is that when you go to your downloads, so in this case, if I go to my downloads, it has been downloaded as HTML file. The previous one was downloaded as R. So for the HTML file, what that means is that you will get it exactly like the Jupyter Notebook, just that now you can't edit the code, but you can copy it into your RStudio. Okay, it means you have access to everything, just like read only, and all the links are clickable. Everything is still clickable. Yeah. So that's the beauty about the Jupyter Notebook. So I would say by far it's the best, and it can run different programming languages at the same time. So at the moment I am using R, but naturally it was done it was by default, it makes use of Python. So here it is making use of Python. If I want to use R, then I have to switch the kernel to R. And if I wanted to do C++ and other programming languages, I just needed to add that kernel to this, and I can run those programming softwares as well, or languages as well. Okay. All right. So basically, this is just to say that on the channel, it depends on what you are looking for. So if you want to get a good understanding about statistics, a good understanding about how to know the right statistical method for the right job, that is a good place to start, is to go through quantitative methods for research and all the recent videos that I've done, because I've recently I've recently done similar sessions with other student bodies. So, for instance, mastering feature selection, unlocking complex research, introduction to analysis and forensic insight, and all those things. Yeah. So, please, it looks like there's Can you please mute everyone, please? Hello. Okay. Please, can you hear me?
Yes, please.
Yes,
Yes,
we can hear
Hello.
you, doctor. Sorry about the
Okay.
feedback.
Yeah, I can hear
No,
you.
no worries. All right. So basically, what this is to say that when you go to the channel, it depends on what you want. If it's about programming from scratch, then you start with the first video. Okay, then you progress. And then the Jupyter notebook I was just talking about, there's a whole video on how to switch from R Studio to Jupyter notebook. So you can also watch that. And I'm sure by the end of today's meeting, you fall in love with Jupyter notebook. That is actually what I've been using for all my previous sessions with NUGS-CHINA and all the other, because it makes teaching quite handy and easy. So that's why I make use of that. Yeah. So, and there are so many intro to statistics on the channel, including advanced methods. So when you just go there, you just explore. So I would advise that you probably start with the introduction to statistics. I did these 4 was done for Oxford University students and staff. So you can start with that. And then recently I did one for another student body. I think that's empowering women researchers in STEM. So all the videos on empowering women researchers in STEM is just similar to like it was a master class, and just that we also learned how to use statistics to solve a forensic research, which was quite interesting. Like imagine you are using statistics to help us to determine the kind of weapon that was used to cause and inflict some wounds on some individuals that we didn't know anything about. Yeah, so it's quite interesting. So there are so many interesting stuff there. All right. So now coming back to what we are going to do today. So like I said, just a quick recap is that we are going to I'm going to talk a bit about some of the advanced statistical methods and a brief introduction to the statistical programming, and then we'll look a bit into some practice tasks. But the practice task, it appears, I'll just give a brief intro. I couldn't wrap up all the codes because I was time bound. So we'll see what we can do when we get there. So for the generalized linear models, it's basically just regression models that are applied to cross-sectional data sets. So remember that when you talk about data structure, so there are 2 types of data structure. So it means that when you're going to do analysis and you want to know the kind of statistical methods you should use, especially when we talk about regression, there are 2 important things. One is to know the nature of the data structure and also the nature of the dependent variable. So it means that for regression, we have some dependent variable or some outcome variable that we want to see certain factors that predict it. Okay, so it means that for regression, we are always looking at a one-dimensional association of some set of predictors on that outcome. Okay, so what I mean by a one-dimensional, it means that it's just a straight line. So that's what I mean by one-dimensional. It can be more complex. Okay, but the emphasis is we apply it to cross-sectional data. So the question is, what's a cross-sectional data? Anytime you have a data with several variables, and each row of the data correspond to a particular subject or individual, meaning that each individual has only one row in the data, that is a cross-sectional data. It means that those data where we didn't follow an individual over time, then it becomes a cross-sectional. It doesn't have to be only about humans. It could even be about just any data where for each ID, the ID could be about humans, it could be about any subject. Once the ID, each ID has just one row of the data, then that makes it cross-sectional. And for cross-sectional data sets, the regression models that we apply on the cross-sectional data set are called fixed effect regression models. And now for those fixed effect regression models, that's why we are calling it as generalized linear models. So it means for the generalized linear models, it is also considered as fixed effect regression models. And remember that they are fixed effect because it's applied to only cross-sectional data sets. Fine. Now, so it means that in order to determine the choice of model, even for the generalized linear model, the first thing is the data structure. If the data structure is not cross-sectional, but rather longitudinal in the sense that a particular individual could be followed at multiple time points, or a particular individual would have multiple rows of data in the same data set, then that's a cross-sectional data. Others call it panel data. So if you hear of panel data, it's the same thing as cross-sectional, longitudinal data, sorry. And so for the longitudinal data set, those are, if you want to model longitudinal data set, then you need to use something called mixed effect regression model. So that is the second part. So the mixed effect models is just the same generalized linear models, but applying it to longitudinal data sets. Okay, so for the generalized linear models, now we've learned that either the mixed effect or the general linear models, they are two, how do you call it? They are two important information you need to know. One is the nature of the data structure, and then the next one is the nature of the outcome variable. So please, if you have questions, what I'll advise is that rather maybe save the question, just write it down, and then at a point I would let me finish the first phase. Now we have like 3 phases. So let me finish the first phase, then I'll take questions. Then we'll go to the second phase and the third phase. Yeah. So that I can answer all your questions. Fine. So for the generalized linear models, like I said, apart from the data structure, the next thing is the nature of the dependent variable, not the nature of the predictors. So the predictors could be continuous, could be discrete, it could be categorical. We don't care. It's rather the dependent variable. If the dependent variable is categorical, it introduces some class of models called logistic regression models. And if the categories are just 2, that's a binary or binomial logistic. And if the categories are more than 2, that is 3 or more, then we have a multinomial logistic regression model. Even with that, we could also have situations where the categories have natural ranking in there. Like, let's say if you're talking about grades of infection, where we could have grade 1, grade 2, grade 3. It's categorical, but there's some ranking in there. That introduces something called ordinal logistic regression. And then the logistic models estimates odds ratios, but there are instances where you are interested in estimating risk ratios. So there's another class of model called log binomial regression. So the log binomial regression is synonymous to the logistic regression, but it is used to estimate risk ratios, especially situations where you are rather interested in quantifying the risk and not the likelihood of experiencing an event. So the likelihood of experiencing an event can be quantified based on the odds ratios, but the risk ratios would help you to rather quantify the risk. Okay, so that is one thing you should note. And then if the dependent variable is continuous, it introduces to some class of models. We have the OLS regression, ordinary least square regression. We have generalized least square. We have quantile regression and COVA, and so on and so forth. And if the dependent variable is count or discrete in nature, then it introduces us to some class of models called Poisson class of models. And for Poisson, it has some parametric assumption that the conditional mean and variance of the outcome should be equal. If it is not equal, then it means there's dispersion in the data. If the mean is greater than the variance, it introduces over dispersion, and if it's less, under dispersion. And in the case of dispersion, when the mean and variance are not equal, then quasi-Poisson and negative binomial regression becomes the next alternatives. So this is just to say that even for the fixed effect regression models, where the data is cross-sectional, the nature of the dependent variable, whether continuous, discrete, or count, that continuous, discrete, or categorical, introduces the class or tells the choice of models you can use. And if the data is cross-sectional, so it means once you are given a data and you want to do regression, don't just go ahead doing the regression without first of all knowing the structure of the data, whether it's cross-sectional or longitudinal. Remember, if you apply cross-sectional data, if you apply fixed effect regression models to a longitudinal data set, it means the data set was longitudinal, but you are assuming it is cross-sectional. That is wrong. So it means that anytime you mistakenly use a fixed effect, let's say Poisson regression, to model, let's say, number of road accident factors predicting number of road accidents in, let's say, in a certain country, right? In that case, remember that you are telling the model that even though the data is cross-sectional, where individuals have multiple rows in the data, you are telling it that it should assume that each row of the data corresponds to a different individual. So it means that it is going to be a statistical suicide if you apply fixed effect regression models to what? To longitudinal data set. Fine. Now, I just talked about, and this thing I've already touched comprehensively on my YouTube channel. Now, when you talk about the longitudinal data set, there's also another data structure I want you to note. So it is not all the time that data is what? Data. So remember, when you talk about cross-sectional, we are saying that each individual has what? A single row of the data, right? A single row in the data. That's fine. But you notice that what makes it cross-sectional is also that we are collecting several information at the same time. Okay. And we have even different types of cross-sectional. We also have something called pooled cross-sectional. So if you go to the YouTube channel, I think I've covered that extensively. So I don't want to go much into that because that's like a whole lecture. Who is writing on that? I don't know how this thing came up on. Is it possible the person could erase it or something? Okay, it's fine. I think I should be able to erase it from here. Okay. All right. So, can you hear me, please?
Loud and clear,
Yes,
sir.
please.
Yeah, we can hear you.
All right, thank you.
Yeah,
Okay,
we are
so
very good.
okay, that's fine. So now for the mixed effect models, okay. So the mixed effect models, remember that it is used to model two things, two kind of data structure. One is longitudinal data, and two is the hierarchical data set. Okay, hierarchical data set. So what is hierarchical or nested data? So you notice that, so for instance, let's say you are collecting data on patients, where each different set of patients or some set of patients were taken care of by a particular doctor. So you have a variable called doctor ID, where let's say if the patient are about 600, about 100 of them were taken care for by a particular doctor. So we have that kind of data. And let's say if these patients were also selected from different district hospitals or different hospitals. So it means patients are clustered under doctors, and then they are also clustered under hospitals. So that's like an example of a hierarchical or nested data set. So it means that a nested data, you can think of a nested data as situations where we have hierarchies in the data set, such that you have the subject, and the subject too can be classified into, let's say, if it's about, how do you call it? Even populations and census and so on and so forth. You notice that we have citizens or individuals, and the individuals might belong to some specific communities or towns, and the towns might be nested under different districts. District might be nested under different regions. Regions might be nested under something else. Yeah, and so that's like a typical example of hierarchical data set. So it means another name for mixed effect model is also hierarchical linear models or hierarchical linear regression. And another name is multi-level regression. So if you hear multi-level regression, it's the same thing as hierarchical linear regression. Now, there is something I want people to be aware of. There is something called hierarchical regression, and there's something called hierarchical linear regression. So the one without the linear component is actually situations where, let's say you have, I've already covered that on the YouTube channel. I think if you watch this video, I think, yes, this video. So if you watch this video, you know that the distinction between that. But basically, there are instances where you have, let's say, 5 predictors, and you want to see how they predict the outcome. But instead of putting all the variables, the predictors in the model and fitting it just like we often do, you want to do it in a stepwise fashion. So you first of all put the first predictor in the model, you fit the model, and then you put the second one into the model. So meaning there's already a variable, a predictor in the model. You put the second one, and there are instances where the previous predictor was not significant. But after adding the second one, it made it to be significant. It means that new variable could be a potential what? A potential mediator. So it means the hierarchical regression is a way of identifying potential mediators or moderators. I don't expect you to understand the mediators and moderators now. I think I'll talk about it a bit, but again, I've already covered that as well. So if you watch, I think one of either this video or that video, the part B of this introductory session 2, or the part A, I think I've covered that extensively there. So for the how do you call it? So for the hierarchical data, so this is just data which is nested, okay, nested within itself, and so it means there are high level nested levels, okay, in that data, and then so it means we can have a data which is nested and also collected over time. So you could have a longitudinal, hierarchical, or nested data. Again, the mixed effect model can handle that. So with the previous hierarchical regression as a model selection or as a model fitting criteria, I think what I was trying to explain was that you don't put all the variables, the predictors in the model at the same time. You do that in a stepwise fashion, and at each stage you evaluate the model and the R square. And then when you add the new one, you check whether the change in R square was significant or not. If it wasn't significant, then it meant that the new addition did not improve the model. I'm not talking about whether it increased the variable, the R square, because if you have a model with one predictor, if you add a second one, automatically the R square will increase, even if the second predictor is significant or not. However, if the change in R square is significant, then it meant that the new variable was a significant improvement of the model. And so with that, it helps us to identify potential mediators. So a mediator is a situation where a certain predictor was not significant or didn't have significant effect on the outcome, but in the presence of another variable, it became significant. So it means that that variable does not have a direct effect on the outcome, but it has an indirect effect or indirect significance in the presence of a certain third variable. And that third variable is a potential mediator. And there's something called moderators. So moderators are situations where you have, let's say, some predictor has an association or an effect on the outcome. The effect could be positive effect or negative effect. And then in the presence of a third variable, that association either increases or decreases, or the direction of association could also change. So it means there are situations where in the hierarchical fashion, you added the first predictor into the model, which had a negative effect on the outcome. But after adding a third variable as the next step, it caused the variable which was positively and negatively related to the outcome to become positive, or it caused the R squared to significantly increase. So it means that in that case, that third variable has increased the strength of association. Or let's say if it rather decreased the R squared, then it means that it has also decreased the strength of association. So moderators either decrease or increase the strength of association between a predictor and the outcome, or it could also change the course or the direction of association. So, and that's why people use hierarchical regression, the one without the linear aspect. Okay, so remember, hierarchical linear regression is the same thing as mixed effect models, but without the linear wording, that hierarchical regression is just like a stepwise regression. Okay, it's like a stepwise regression. But that one is often employed when you want to explore much more complex dynamics of the association, identifying potential moderators and mediators. If something is found as potential moderator and mediator, you can now do a proper moderation mediation analysis to check that. When you combine hierarchical linear regression, when you combine that hierarchical or stepwise regression with a moderation mediation analysis, then you don't need to do anything about structural equation modeling. So structural equation modeling, mostly before people do structural equation modeling, and we are going to talk about that later on, and you are not even sure about the kind of structure, you can use hierarchical regression. That's that hierarchical stepwise regression. Let me use stepwise in there, that so that it makes it easier. So hierarchical stepwise regression. If you couple that with moderation mediation analysis, you'll be able to identify any hypothesis, any complex hypothesis or relationship you want to investigate without even having to use structural equation models. But those who use structural equation models, when they are not too sure about the kind of structure or hypothesis they want to test, they use the hierarchical linear regression coupled with moderation mediation analysis as a preliminary analysis before the structural equation modeling. So this is just something I wanted you to know. So don't confuse hierarchical linear regression with hierarchical stepwise regression. They are two different things. So the hierarchical linear regression or the multi-level regression is the same thing as mixed effect models. And we said mixed effect models can be used to model either a data which is what? Longitudinal in time, or two, a data which is nested in time, nested in terms of nested or hierarchical levels, and also a data which is nested, but also what's collected over time, right? So that's basically, so it means that the mixed effect model is a generalization. So anytime you want to do repeated measures, like a data where the dependent variable 2 has multiple time points, so that's a perfect example of a longitudinal case. So it means all repeated measures data can also be modeled with mixed effect regression model. So anytime you want to do repeated measures ANOVA, remember you can also use mixed effect regression for that by treating the multiple time points as a random effect, and then if you are trying to compare that between some groups, then you put the group as a predictor in the model, and then the outcome variable is the dependent variable, and so on. So for mixed effect models, it has two things that you need to be aware of. So we have the fixed effect and the random effect. So those two combines to form what we mean by mixed effect. The first phase, we said the generalized linear models is just fixed effect models that is applied to just cross-sectional data, right? Now for the mixed effect, we are saying that mixed effect has two components. We have the fixed effect and the mixed effect. The fixed effect are those predictors of interest. So it means that predictors of interest will automatically be considered as fixed effect. And then the random effect variables, they are the variables that talk about the structure of the data. So it means the random effect variables, they are the variables that are not predictors of interest, but they talk about the structure of the data. By talking about the structure of the data means that there are variability in the data set, and those variability in the data set are due to those variables. So for instance, if data is collected over time, it is collected over time because we believe that the data might change with time. So it means time adds some variability or variations to the data. So in that case, even though time is not a predictor of interest, I have to add time as a random effect to account for the temporal pseudo replication or the temporal effect in the data. Okay, so in that case, you add time as a random effect. And they are also, so in this case, when they are those variables that are the high order hierarchies. So if you have doctors, if you have, let's say, patient nested under doctors, they will put doctors as the doctor ID as a random effect, even because it's not a predictor, but it tells that the patient were clustered or nested under doctors. So in that case, you have to add that as a random effect. Okay, so it means that, and not just that, anything. So for instance, spatial replication. Imagine if we're collecting data at some specific locations over time, then it means there could be spatial effect. This is to say that the data you are going to see at a particular location might vary from one location to the other. So it means location is contributing to some variability to the data. And any source of variability, any variable that is contributing to any source of variability is a potential what? Random effect variable. Okay, and that is just talking about the structure of the data. So that is how robust mixed effect models are to modeling both longitudinal data sets and then hierarchical data sets, or both. All right, and the last one is what we've been collecting data and we add patient ID or subject ID. We do believe that if you add patient ID as a random effect, it is trying to do something very magnificent. So for instance, if you add patient ID as a random effect, it accounts for something you call individual heterogeneity. This is to say, situations where, let's say, you are trying to predict some outcome, okay, but you believe that the patient can be very different. Maybe the differences you are seeing could be due to the fact that they have different immune response. They have different, there are some external variables or external factors that are contributing to certain variability in the data that we don't know about. So adding patient ID as a random effect is trying to tell the model that it should treat each patient as different. This is to say that it should assume that there's some external factors that are also accounting for additional variability across patient or between patients. So it should treat it as such. Okay, so that's also one of the beauties about adding patient ID as a mixed effect, as a random effect in the model. So that is all about the mixed effect models. So the mixed effect models is the same generalized linear model. So all the generalized linear models I mentioned here about the logistic models, the Poisson class of models, the OLS class of models is the same thing, but this time around you are applying it to a longitudinal or a nested data set. And that and then in R, there are specific functions to perform that. So if you want to do anything now, we are in the global world. ChatGPT is there, and you can even go to Google. If once you're able to import data into R, you don't even need anyone to help you. The rest is just making use of online resources and you'll be fine. Okay, so that's it. Every good programmer, you don't have to stress yourself if someone has already developed a package to do something. Okay, it's only when you are learning how programming skills. So for instance, on the YouTube channel, you see like a video on creating complex functions in R, like how to write your own functions in R. That sometimes is very useful, especially those who are doing your PhDs, doing simulations, those who are doing complex stuff that there are no packages for. You should be able to write your own functions to do certain things. Even in this particular, when you get to the practice session, you notice that I had to write my own functions to do certain things that there are no existing packages for. Sometimes by making use of existing packages to still modify or create your own functions as well. All right, so this is the first two class of models I want you to know. So these two are regression models, okay? So I want you to note that. But there's a disclaimer I have to give. So most people from non-statistical backgrounds usually confuse multivariate regression with multiple regression. So let's try and understand the difference. So one thing is this: anytime we have a single predictor, and then a single outcome. So let's assume that the outcomes are just one dependent variable you want to predict. Okay, for instance, you want to predict infection status. You want to predict, let's say, immune response. You want to predict student performance based on their GPA and so on. So just a single one. So now we are assuming single dependent variable. The moment the predictor is just one predictor, that is what we call a simple regression. So whenever you hear simple means that there was only one predictor. But the moment there are more than one predictors in the model where the outcome is just one, that is what we mean by a multiple regression. So you can call it multiple linear regression because the model is a linear model. We could have a non-linear model, situations where you believe that the variables have non-linear effect on the outcome. Then in that case, you can have non-linear or polynomial regression models. Those also exist. Okay, there are instances where you are still using a linear model, but there's a particular variable that has a non-linear relationship with the outcome. So maybe it has a quadratic relationship with the outcome after you did the scatter plot. So in that case, one could decide to add a quadratic term to the model, and it's still a linear model with a quadratic term, fine. But that's not what I'm trying to talk about. What I'm trying to say is that let's assume we are using linear models. So for the linear models, situations where you have more than one predictor in the model, that is what we mean by a multiple regression. The moment you hear multivariate regression, it means that there are more than one dependent variable. So multivariate applies to the dependent variable, whilst multiple and simple applies to the predictors or the independent variable. So it means I could have a multivariate simple regression. So a multivariate simple regression will be a regression model which has several dependent variables, but only one predictor. So that's a multivariate simple regression. So I could have a multivariate multiple regression where we have several dependent variables and several predictors. Okay, so these are something I want people to understand, especially when you talk about survival analysis. We'll get to that point, and I'll tell you the mistakes people have been making about calling something multivariate survival analysis, which is very wrong. They meant to say multiple. Another best way to call multiple is multivariable. So if you don't want a problem, you could call it multivariable regression or multiple regression. Multivariable seems to be like a better wording in situations where you feel like multiple doesn't look too much sounding, especially when they talk about survival analysis. So we'll come there. So again, at this phase of the presentation, we are just introducing some of the existing modern statistical methods out there and when and how to use them. All right. So the next one is there are a class of models called machine learning methods. Okay, so I'm sure most people have probably heard about it in recent times. So deep learning and we have machine learning. They are a bit distinct but similar. And remember that when you talk about machine learning, one thing I want you to notice that it depends on the area of application. Depending on the area of application, the class of machine learning methods will be different. So it means if you are talking about time series analysis, we have machine learning methods specifically for time series analysis. If you are talking about facial recognition, voice recognition, how to depending on certain characteristics of an individual, you want to be able to determine whether that individual is so for instance, let's say if you have captured your face, okay, and then you are, especially when you are going through the airport or anywhere they apply facial recognition algorithms. The whole point is underneath those algorithms are machine learning techniques going on there, okay, or deep learning methods and underpinning those algorithms, such that it's helping us to predict if you are indeed that individual or not, right? So I'm just trying to say that the class of machine learning I'll use for classification problems will be different from the class of machine learning method I'll use for facial recognition or voice recognition or even natural language processing. They'll be different. Okay, so I'm just trying to say that machine learning methods are very wide and it depends on the area of application. Okay, fine. But when it comes to regression, all the regression models we've mentioned, okay, the generalized linear models we've mentioned, we have its machine learning equivalent. So for instance, classification tree and decision tree, they are the basic machine learning regression methods, okay? So what they do is that they fit models, but present models in the form of a tree structure. So it means unlike the classical generalized linear models or the generalized linear mixed models, okay? The generalized linear mixed models are also the mixed effect models, okay? And we just learned that they are also known as multi-level models or hierarchical linear regression. And the hierarchical linear regression is different from hierarchical stepwise regression. We've learned that, fine. Now, for every generalized linear model here, we have its equivalent machine learning technique. So classification tree is where the dependent variable is what? Categorical. And then we have decision tree, where the dependent variable is either continuous or discrete. So in that case, it allows you to choose the error distribution, whether Poisson or whether continuous. Okay, fine. So mostly continuous are Gaussian, fine. So it means that we have classification tree and we have random forest, gradient boosting machines, support vector machines, and so on. So these variables are also able to model much more complex relationship, including nonlinear effect. Remember, with the generalized linear models or the generalized linear mixed effect models, naturally, we expect each of the predictors to have a linear relationship on the outcome. But in real life, it is not always the time. That is why sometimes some of the regression model fails to satisfy certain parametric assumptions. So this is to say that situations where a particular continuous predictor has a nonlinear effect on the outcome after you did a scatter plot, okay, you've realized that the relationship between a particular continuous predictor and, let's say, a continuous outcome variable was a bit nonlinear. Then what other researchers tend to do is that they fit something called splines to those predictors with nonlinear relationship on the outcome to smoothen out that nonlinear effect to make it fairly linear. And that alone introduces another class of regression models called generalized additive models. So it means the generalized additive models, we have the fixed effect and the mixed effect. So you could have generalized additive mixed models, or if you just hear generalized additive models, that's the fixed effect. So the generalized additive mixed models or the generalized additive models is just the same GLMs we've talked about and the GLMM we've talked about, However, the only difference is that it is allowing us to fit splines to those predictors that have nonlinear relationship on the outcome. So that is another alternative to nonlinear regression. Okay. So it means that instead of me using nonlinear regression, I'm imposing a linear effect on that variable with nonlinear association on the outcome by fitting splines to it. Example of such splines, we call one of the examples is these splines, and it will smoothen out the nonlinearity to make that variable, the transform variable, to be fairly linear on the outcome. And then you can now predict, because remember that the linear regression is assuming each of the predictors have a linear relationship on the outcome. If that is not the case, you have to now think about an alternative. So machine learning is just state-of-the-art methods that are used to that applies deep learning techniques and machine learning techniques to also perform these class of regression models. And like I've already given a disclaimer that the choice of machine learning methods will depend on the area of application. For time series, so for instance, let me see. So for time series, I thought I added a paper to it. So for instance, let me just go to Google Scholar. So let me type, okay, fine. So this is like one of my publications where which is published in one of the top K1 journals in forecasting. Okay, so here you learn that we're using machine learning techniques for forecasting and backward prediction in time. Okay, and it was first of its kind. It's quite a bit mathematical heavy, but not very yeah. So you notice that the class of models outlined there, you can't use it for regression. It's just for time series. Okay, so that's basically what I'm trying to explain with the difference. Okay. Now, the next one I just want you to talk about, for us to talk about, is survival analysis. And today's practice task was going to be based on that. So for survival analysis, this is used to model time to event outcomes. So situations where, let's say, especially those in medicine, we use that a lot. Those into clinical trials, they use that a lot. So for instance, let's say situations where you are looking at the time to an individual dying from an infection, or maybe the time to an individual experiencing an adverse event in a study, or the time to an individual withdrawing from something. So it's just, or time to relapse, okay, or time to remission. So so it means that anytime you are looking at time to event outcomes, remember we often call it survival analysis, okay, or sometimes the data, we call it survival data. But remember that it is only because the original, the whoever developed survival analysis for the first time was applying it to an outcome which was time to survival. So ever since the person who developed these class of models applied it to an outcome which was time to survival, it has now made it somehow get the name survival analysis. But sometimes I'm just trying to say that it doesn't mean that it is only used for only studies that are about survival. No, it could even be time to a machine breaking down. Okay, so that's why the better wording should be time to event analysis. That would be like a generalization, so that survival analysis will just be a subset of it. But unfortunately, whoever developed the method applied it to survival, time to survival, and that's why it picked that name. So with that, we have something called Kaplan-Meier analysis, which is a non-parametric analysis. Which is a non-parametric analysis. So what it does is that it's a univariate analysis. This is to say that for Kaplan-Meier is situations where you want to visualize survival curves, okay, between some categories, okay. So it means that if, let's say, I'm looking at time to survival or time to death, okay, and I'm comparing the time to death between males and females, then I'll have a certain 9 survival curves stratifying it or distinguishing between males and females. And that kind of graph or those survival curves are obtained from what we call Kaplan-Meier analysis. And they are univariate because you can only look at one categorical predictor at a time. You cannot apply Kaplan-Meier to a continuous predictor. Before you will be able to apply to a continuous predictor, you have to categorize the continuous predictor in order to use Kaplan-Meier analysis on that. Now there's an extension. So here, like you said, you notice I said univariate. Okay, univariate is a univariate survival method because it's only considering. So remember at this stage, the outcome variable is just one time to event outcomes. Okay, just one time to event outcome. So it is only one dependent variable. So it's univariate. But here I'm using the univariate also to refer to the fact that it has only one predictor at a particular point in time. And then we decided now to extend that, and it gives rise to a semi-parametric method called Cox proportional hazard models. Okay, so the Cox proportional hazard model is a regression model. Okay, it's a regression model, just that the outcome variable is a time to event outcome. And with that, you can now look at several predictors, how several predictors predict the outcome. Okay, fine. Now, for the Cox proportional hazard model, it is used to estimate hazard ratios. Okay, and there's a parametric assumption. There's a particular strong assumption that needs to be identified. So there is something called a proportional, just as you said, as the name goes, Cox proportional hazard. So it means the hazard ratios or the hazard must be constant. But the moment the constant hazard or proportional hazard assumption is violated, we have other methods that we use. Fine. But here, the disclaimer is that most biologists or clinicians call the Cox proportional hazard models as multivariate survival models, which is very wrong. Okay, it's not multivariate survival model. They are calling it multivariate because they are confusing it with multiple regression. Like I said, multiple means several predictors. But because the Cox proportional hazard allows you to look at several predictors on the outcome, they are calling it rather multivariate regression. It is not. Rather call it a multivariable survival model. In that case, you don't have any problem. So call it a multivariable survival model. If you call it multiple survival model, maybe it will look a bit ambiguous. So rather call it multivariable survival model, but don't call it multivariate. The moment you tell me multivariate survival model, you are trying to tell me that you are jointly modeling two time to event outcomes, two or more time to event outcomes. And currently we don't have existing methods to do that. Okay, so there's nothing like multivariate survival models at this stage, but we have a multivariable survival models. And there's an extension called multi-state Markov models, I also have like a paper that involved or employed the multi-state Markov model. It's in a Springer Nature journal. And so I will explain briefly what the multi-state Markov model does. So the multi-state Markov model is just a generalization of the standard survival models. So anytime you hear standard survival models, we are talking about Kaplan-Meier and the Cox proportional hazard models. For Kaplan-Meier, once you get the survival curves between the categorical predictors, okay, you can check whether there's significant difference in the survival curves. And the popular test we use is called log rank test, which is a popular test that we often use for that. Okay, so don't do Kaplan-Meier analysis without a log rank test. Okay, because remember, we can't make inference based on descriptive statistics. So it means that once you produce a graph for me, or you produce central tendencies, the mean, median, mode, and those things, you cannot make an inference from it. Okay, you cannot say that because the survival curve of males appears to be higher than females, then it means there's a significant difference. No, you cannot talk about significant difference as far as until you do a statistical test. And that's what we mean by inferential statistics. So statistics is broadly classified into descriptive statistics and inferential. For the descriptive, is just to summarize the data, either graphically or by certain summary measures, okay? But if you want to now make an inference or a conclusion with confidence, that confidence is quantified by confidence levels, and that introduces what we mean by inferential statistics. So all the regression tests, all the statistical hypothesis tests, and then all the statistical models collectively are what we call inferential statistical models, inferential statistical or inferential statistics, basically. All right, so anytime you hear inferential statistics or inferential statistical methods, we mean statistical tests and statistical models. And for statistical tests and statistical models, they are different. For regression, it's a model because there are certain unknown parameters that we need to estimate. ANOVA or t-test is not a model. It is rather used to just test the validity of some hypothesis. So it means that whenever we are talking about hypothesis testing, we don't estimate any parameters. So that is why that is called test. And then for models, we estimate parameters. And that is why it's called what? A model. So it means that don't confuse statistical tests with statistical models as well. All right. And so with this classical survival analysis, you notice that it has a certain weak assumption. So for instance, let's say if you are talking about time to what? Death. If time to death is the dependent variable, okay, for our survival analysis. Now look at this. You notice that there are situations where an individual, okay, who entered the study can undergo different possible transitions before death eventually occurs. So for instance, an individual could be healthy and later on get a mild infection and later on transition into a severe infection. But someone at severe after some future time can maybe come back to mild, and someone can even at mild can become healthy, and someone from healthy can go back to mild infection, and from mild can go back to, let's say, severe infection and eventually die. But the standard survival models ignore those history. It only looks at the end of the study, was the individual dead or alive? So it means it throws away all the information about possible disease transitions that an individual actually make over the course of their infection or before death eventually occurred. So the multi-state Markov model extends these traditional models by capturing those possible transitions that occurs. And this particular paper of mine was applying that to how do you call it? Was applying that to where is it? Okay, was applying that to a biological data. Okay, so I mean you can take time and go through that. Yeah, but today the goal was to develop a code for that to a medical application problem we wanted to solve together. I always like to wrap my sessions with an application and in R, and always it's not just any application but something meaningful that you could also even base on it and develop research problems and research topics and so on. But unfortunately, time couldn't permit me to wrap up or finish up the course because I was a bit lazy, and I'm sorry, but I will see what I can do. The course for this one is, I think, is online, but I will see what to do. All right. So basically, that is one thing I wanted you to note about the multi-state Markov model. And remember that sometimes, let's say, now every time people are doing research and people want to publish high impact publications, but we do believe that if you know and understand a certain statistical model, you can base on that model to design a study, and that study will be novel for the first time in your area. Multi-state Markov model is underused. Many people don't even know about it. But the truth is that it is the most realistic way to model a survival data. Okay, like I said, the classical ones ignore all the possible transitions that occurs. And we'll look at an example during the practice session. Okay, so the next one is structural equation modeling. I won't talk much about it because I've already covered it on my YouTube channel. But you notice that for generalized linear models, the generalized linear models, I can call it fixed effect linear models, okay, because I said they are fixed effect because the data is just cross-sectional. Okay, and then the mixed effect, I've already explained it, fine. Now, these regression models, even including machine learning regression models, is assuming that the dependent variable, okay, it's assuming that the dependent variable has a one-dimensional association on the outcome. But now look at this. Let's look at this example. Now, so the code here, it means that you can use R to create conceptual frameworks. So that's one thing I wanted you to note. So for instance, so that's, you see, if you look at the Jupyter notebook, you notice that all these are programming codes I've been doing. And I don't need to go and save it in a separate folder somewhere. It tells me that anytime I want to retrieve anything, I just click on what I'm interested in and I get back all the codes and everything, fine. So for instance, I used the, how do you call it? R, okay, to construct this conceptual framework. I didn't have to do it in PowerPoint. Okay, so I'm just trying to say that R is that powerful and you can use it for anything you want. Just search for it if you want to know how to do that. Okay, fine. So now here, now let's look at, so in a one-dimensional case, I was going to look at how, let's say, psychological well-being, work engagement, and let's say job satisfaction predict, let's say, burnout. Okay, if burnout is an outcome. In that case, it's just a one-dimensional association or the one-dimensional effect of these predictors on the outcome. But situations where I want to now explore much more complex, associations in order to answer multiple hypotheses at the same time. So, for instance, here I could have multiple hypotheses. Like I want to know whether, so for instance, here I'm looking at whether job satisfaction mediates the relationship between work engagement and burnout. By mediating means that in the presence of job satisfaction, work engagement would have a positive, association with burnout outcome. In its absence, it will not. So that's what we mean by a mediator. Okay. And there is, and I think I've explained what a moderator is. So for moderators, they either increase the strength of and direction of association. Okay. They either increase or change the direction of association. Okay, fine. Okay, so that's basically that. So what we use structural equation modeling for is to now investigate much more complex or extend the classical one-dimensional association to multiple ones. And the beauty is that you could even model or have more than one dependent variable in the same structure. So for instance, here I have two different dependent variables. But if we want to now model two different dependent variables, especially for the fixed effect models, we have existing methods called multivariate regression. So it means the multivariate regression allows you to model. So for instance, situations where you are looking at some set of predictors, how they predict a certain outcome, and you are using the same set of predictors. You want to know how that same set of predictors predict another outcome variable. You don't have to do it separately. You can combine it using the multivariate regression. So multivariate regression would literally fit separate regression model and account for the relationship between the two dependent variables. If the dependent variables are even three, so it means you are looking at the effect of the same set of predictors on three different outcomes or three different dependent variables. Then it means that the multivariate regression will fit different regression models and also account for the relationship between the dependent variables. Okay, but if you fit separate ones, okay, without, so meaning that if you use, let's say, a different model for each of the outcomes, you didn't account for the relationship or the associations between, or the correlation between the dependent variables. And somehow it can affect the estimate, especially if you're looking at the same set of predictors on those outcomes. So as a matter of fact, that tells us that even when it comes to hypothesis testing, where you want to do t-test or you want to do ANOVA, you notice that for ANOVA, you have a particular continuous variable and you want to see how that continuous variable differs between three or more groups. What if you have more than one of that continuous variable? Let's say you have about three different continuous variables or three different outcome variables, and you want to see how each of them differs between three or more groups. You don't have to do separate ANOVAs. You have to, first of all, do something called a multivariate ANOVA, and that multivariate ANOVA is called MANOVA. So when you do the MANOVA, and MANOVA concludes on significant difference, then it means that at least one of those predictors was significantly different. Then you can now go and do the separate ANOVAs. But imagine if you do multivariate ANOVA and it says that there's no difference. Sometimes it can save you fortune or time, especially those who are into bioinformatics or those who do a lot of proteomics data analysis or genomic data analysis and so on. You notice that there are instances where you have so many protein expressions, or let's say so many variables, not just, sometimes it could be about 500, 300, and you wanted to do separate ANOVAs for each of them. That is too much. So what that means is that imagine if you do that multivariate analysis and it concludes that there's no difference, okay, at the multivariate level between the three or more groups, then it saves you time. You don't have to now do any how do you call it, individual ANOVAs or separate ANOVAs in that instance. Okay, so that's one of the advantage of doing that. It's just like you trying to do pairwise comparison after you do ANOVA. If ANOVA concludes there's a difference, that is the only instance you now have to do that pairwise comparison. But if ANOVA concludes there's no difference between 3 or more groups, it means that if you even do pairwise comparison, you not see any difference between any pair. Okay, so it means once the ANOVA is not significant, then there's no need for pairwise comparison. The same thing when multivariate ANOVA is not significant, then there's no need to do separate ANOVAs, because it means that none of the separate ANOVAs will be significant, even if you do it. Okay, so that's one of the things I wanted you to know. But for structural equation model, you can even model 3 or more outcomes at the same time and look at complex associations and so on and so forth. And before you do structural equation modeling, remember, you can apply the hierarchical stepwise regression and the moderation mediation analysis as an alternative. Or people can do that first before they do that, especially if you don't even know how this structure should be like. So you can use the hierarchical regression, stepwise regression, and then the moderation mediation analysis. A typical example is something called Anderson-Hayes moderation and mediation analysis test. You can read about it, Anderson-Hayes. How do I spell it? So it's Anderson Hayes, especially those who use SPSS. There's a micro, an external software that allows you to add that particular test into SPSS. But R also has the micro is now also available in R. So it means technically it is not in there. It's not like a package you can just install in R. It's a micro, which is an external, more like an external function someone has created, but you can actually call it into R and use it. Those who use SPSS today, it's a very nice micro for that, but I will entreat you to use R for the analysis. Okay, fine. So that's all about the structural equation modeling. Okay, so in a few minutes, I'll take questions before we continue. So the next one is about dimension reduction techniques. Now, I was also supposed to talk about variable selection techniques. Okay, I was also supposed to talk about variable selection techniques. Variable selection techniques. Unfortunately, many people confuse dimension reduction techniques with variable selection techniques. So variable selection techniques is situations where you have so many predictors. Okay, most people who don't work with large data sets, they often don't have that problem. But those who are dealing with observational studies, let's say you went into the health records and then you were interested in some study, and then in the UK we have certain database for health data. Example is biobank, and then we have the CPRD database and all that. So there are so many. It means the GP, data, hospital data. We have database. I think Ghana, they have something they call the DEMS and so on and so forth. So there are so many databases there. So situations where you want to now take a certain data, secondary data, and do your analysis, but you notice that there are several information that has been collected for each patient. Do you put all those variables as predictors of a certain outcome in the model? Remember that there's a certain problem that I needed to tell you. We call it multicollinearity. In as much as we want to see possibly, it means a regression model will do well if the predictors have high effect or high relationship on the outcome. So it means that situations where the predictors have low relationship or association with the outcome, okay, then it means that regression model will not be the very best. Okay, maybe it means that there are certain variable transformations, or there are better models you should consider for such instances, possibly due to violations in some parametric assumptions and so on. Fine. So what we do is that, so that's basically that for the case of regression. So we are just looking at, we want to see high correlation between the predictors, high correlation between the predictors and the outcome. But we don't want to see high correlation among or between the predictors. So it means the predictors, let's say if you have 10 predictors in the same model, that is how come you fit a model and the model failed to converge, or the regression estimates are abnormal and it doesn't make sense. It's because there are high correlation among the predictors. And that introduces a problem called multi-collinearity. Multi-collinearity is a statistical problem we want to avoid. It means that we don't want to see high correlation among what? The predictors. When it happens that way, this is what happens. So one, if the regression model is significant, it means that at least one of the predictors is supposed to be significant. However, in the presence of multi-collinearity, a model can be overall significant, but none of the predictors was significant, and vice versa. Vice versa means that if none of the predictors is significant, we also expect the overall model not to be significant. But in the presence of multi-collinearity, this also happens. And sometimes the model fails to converge. Okay, fails to converge, or the estimates are abnormal. Okay, so basically it means in the presence of multi-collinearity, you cannot trust your regression estimate. So how then do we deal with it? So that brings us to what we call variable selection techniques. So variable selection techniques are ways of selecting the most influential subset of candidates, candidate predictors, or are ways of selecting subset of those numerous predictors so that we can improve model fit. Okay, but not all the variable selection techniques are able to deal with multi-collinearity. So there are standard variable selection techniques that do not deal with multi-collinearity. A perfect example is stepwise, the stepwise forward and backward elimination and selection. Okay, so that's like, so in R, if you fit a regression model and then you just type step of the model, it will do stepwise regression. So the stepwise regression means it will consider different possible combinations of the predictors, and at each stage evaluate something called the AIC. The AIC is archaic information criterion, and the archaic information criterion is used for selecting the best model. So it means if you fit different models of the same kind and you want to know which model was the best, the model with the least AIC statistic is the best model. Fine. So what the stepwise regression does is that it fits range different models based on different selection of predictors in a stepwise fashion, just like the stepwise, the hierarchical stepwise regression I was trying to explain. It does that in a stepwise fashion. And then the last one is always the best because that had the least AIC. Fine. Now, and there's also another one called BIC. So either AIC or BIC. AIC is archaic information criterion, and BIC is Bayesian information criterion. The smaller the value for a particular model, the better. The AIC or BIC would be meaningless if it is only one variable you've actually it is only one model you fitted. The AIC or BIC is meaningful when you have fitted different models of the same kind. The emphasis is of the same kind. So don't go and look at AIC of, let's say, a regression model and compare it with AIC of a certain different model, which is not a regression model, and tell me that the model with the least AIC is the best. No. If you are comparing different models, so for instance, if I want to compare machine learning with classical regression methods like the GLMs or the general linear models with, let's say, random forest, I cannot find AIC. As a matter of fact, I cannot even find AIC for the machine learning techniques. Okay, so in that case, we need a performance metric. An example of such performance metric is like accuracy measures, okay? Or you could use error statistics like mean square error, mean absolute percentage error, and mean absolute deviations for situations where the dependent variable was continuous. And then if the dependent variable was categorical, then you can use percentage accuracy. Okay, and to do that, we often split the data set into training set and testing sets. So you fit the model based on the training set, which should be large enough. And then the testing set is used for cross-validation. By cross-validation means that we will try and predict the outcome on the testing set, the data we left out, and check the proportion or the percentage of times that the predicted classification was equal to the observed or the true classification. And the proportion of times we made the correct classification is called accuracy, percentage accuracy. And that, in that case, is a way to compare different types of models for classification problems, right? So if I want to compare, let's say, random forest or classification tree or gradient boosting machines with, let's say, a logistic regression, then I should rather be comparing their percentage accuracy, not AIC. Okay, so AIC is used to compare models of the same kind, and not every model you can evaluate the AIC. To evaluate AIC, you need to know the likelihood function. You don't need to understand what I mean by the likelihood function, but not every model can have its likelihood function explicitly written. And so that's why machine learning techniques, you can't find AIC, because AIC is a function of the likelihood. If you go online and you type AIC statistics, not now, AIC statistics. So you notice that it is a function of the likelihood function, and not every model not every model that has its likelihood function explicitly evaluated or could be written. Okay, so that's why it's not applicable to all class of models. Fine. So variable selection techniques is just to select subset of predictors that we believe would that we believe would improve model fit. And so one example is we have the recursive feature selection, and we have machine learning techniques also for variable selection. So for instance, we have the brutal, we have even specific machine learning selections that are based on classification to random forest, gradient boosting machines, and so on. We even have simulated annealing techniques and so on. So there are many methods in that case. But the moment you want to now account for multicollinearity, then you use something called penalized regression techniques, like ridge regression, lasso regression, and something called elastic net. So by ridge regression, what we are saying is that, let's say if you have 20 predictors and you want to know which subset of the predictors is the most influential, at the same time accounting for multicollinearity. So what we do is that ridge regression, what it does is that all those all those predictors that are less important, it will set their weight of importance or their regression estimate to something close to zero. Not zero, but close enough to zero. If it is close to zero, okay, then it's just trying to say that it's not important. Then the ones that are farther from zero, okay, so, or the ones with high weight of importance, they are the predictors of high importance. So it means ridge regression is technically not a variable selection. It doesn't necessarily select variables. It allows all the predictors in the model, but it penalizes all those variables that are less important to have a very insignificant regression estimate. And if they are insignificant regression estimate, then it means that it is automatically favoring those predictors of high importance. But a much more brute force or a much more brute version is what we call the lasso regression. So the ridge regression is also known as L2 regularization. So in case you hear of L2 regularization, it's the same thing as the ridge regression. But the lasso regression is also known as L1 regularization. And what the lasso does is that, unlike ridge regression, certain variables of less importance to have a weight of importance close to zero, what lasso regression rather does is that all those predictors, if there are 20 predictors, all those predictors out of the 20 that are not important, it will set the weight of importance or its regression estimate to zero. It will set it to zero, not close to zero, but to zero. To zero means that there could be 10 predictors and only 3 of them had non-zero weight or non-zero estimate. Then it means all the ones with zero estimate, take them out. And the ones that have non-zero estimate, first of all, are the most influential predictors. And at the same time, they are free from multicollinearity. So that's the beauty about the lasso regression. And the elastic net combines these two. So the elastic net combines ridge and lasso regularization or regression together. So it means the elastic net is an L1 and L2 regularization technique. So it means it's applying. So it means some variables would have their weight of importance set close to zero. Some will be set to zero, and some will be having high weights. So that's the elastic net. But the truth is that if it's about selecting the subset of variables that are more important, then the lasso becomes the best option. All right. So that's something I wanted you to understand. So that is different from dimension reduction. Those who do proteomics data analysis, genomic data analysis, like situations where the kind of data you use is quite heavy. By heavy means high dimensional. What happens is that with the dimension reduction technique, example, principal component analysis. Principal component analysis help us to, first of all, kind of combine all those variables into just one. Okay, so it means that, let's say if there are 20 or 300 protein samples. It's combining all of them into one so that the first principal component will be a linear combination of all those variables. And then principal component 2 will be a linear combination of all those variables after taking one out. Principal component 3 will be a linear combination of all those variables after taking 2 out in that fashion. So it means that one thing about principal component analysis is that it converts your data by combining the data in such a way that you have something called principal components. And the principal component, we believe, not that we believe, explains the variability in the data than any individual variable. Okay, so it means that people can even combine data sets into principal component and use the principal component as a predictor in a regression model. So it means if it is a logistic regression model and then you've added some of the predictors as a principal component, you call that logistic model as a principal component logistic regression. So it means anytime you hear principal component attached to any regression model, it means it's a classical regression model, but at least one of the predictors is a principal component. Okay, so remember that principal component can be used for many purposes. Apart from the fact that we are able to use it to reduce the dimension, it also helps us to know variables we could take out. So it means that, let's say if you consider the first principal component, which explains most of the variability in the data than any other variable and also than any other principal component, it means if you look at the relationship between each variable and then the principal component through something called communalities. I don't expect you to understand this. I would have a whole video on YouTube on principal components. Yeah. Today I even thought of considering that as the practice task, but I felt it to be too advanced for some people. So I just wanted to consider something a bit simple. But I don't want to. I mean, I was going to show you an instance of it, but it feels like it's a work in progress yet, so I wouldn't want to share that yet. Yeah, but I'll do a whole video on that. Fine. So with principal component, the first principal component, for instance, okay, if you should look at the relationship of each of the predictors, okay, or the variables that you use to perform the principal component analysis, okay, the variables that have less correlation with that principal component, it means that those variables should be what? It's not important or can be taken out. So the question is, how many variables should you take out? So it means that if there are 20, let's say, variables that you use for the principal component analysis, remember when you're doing principal component, you don't include the dependent variable. And principal component analysis are applied to only numeric data. Principal component analysis are applied to only numeric data. Situations where all the data sets are categorical, then we have something called factor analysis. So factor analysis is the twin brother of principal component analysis, just that it is applied to categorical data sets. Okay. So it means that in certain softwares like SPSS, they will always confuse principal component with factor analysis. They make it behave as if it's the same. It's not the same, but the principles are the same. But the area of application or the kind of data you use is different. Okay, fine. So it means that for the principal component, let's say if there are 20 variables you use for the principal component, it will generate 20 different principal components. If you use 20 variables for the principal component analysis, it will generate 20 different principal components, where the first principal component is a linear combination of all the variables without taking anything out. The second principal component is a linear combination of all the variables after taking one out. The last principal component, which is in this case the 20th principal component, will be a linear combination of all the variables after taking 19 of the variables out. Now, for each of the principal components, there's something called the eigenvalues, and the eigenvalues quantifies the variance. Okay, that is explained by each principal component. The moment the eigenvalue is just above 1, meaning that all those principal components where the eigenvalues are below 1, they should be discarded. Okay, they must be discarded. So imagine if the eigenvalue for each of the principal components, the first one would always have the highest eigenvalue or the variance. So imagine if it gets to the 4th principal component, when it was getting to the 5th, the eigenvalue or the variance was just below 1. Then in that case, it means you should end at where the eigenvalue was just above 1. So if where you are ending is principal component 4, Principal component form means that a linear combination of all the predictors after taking 3 of the variables out. So if you want to now know the variables you should take out, then you go back to the, let's say, the principal component 1 and 2 or 1, and check all the predictors. Which of the last 3 has, or which 3 of those variables has the least association with that principal component? And it means that those variables can be taken out. And that association is actually obtained by something called communalities. And the communalities is just a sum of something called factor loadings. You don't need to understand all these, but there are things that you can easily do. And there are a lot of online information for that. So some of you might be doing certain kind of analysis and you might need to apply principal component. So it means principal component can help you also for variable selection, okay? And it also can account for multicollinearity. The reason is because the principal component, there's no correlation between the principal component. So it means that even though the original variables had high correlation between them, converting it to principal component, then the principal component do not have high correlation between them. So indirectly, the principal component added as a predictor will be free from multicollinearity. Okay, but how do we interpret it? I think I'll have a whole video session on that. And one can also use principal component analysis like a clustering analysis. Although we have set of statistical methods called cluster analysis, they exist. Okay, they are set of. So if you want to know what I mean by cluster analysis, let me see. Just a minute. And don't get scared. I just want you to see how it looks like. Just a minute. So it's like you have a data and we've been able to stratify the data into separate clusters. But we can look at a 3D version and you can see something like this. Okay, so this is what I mean by cluster analysis. It's like we are trying to find distinct patterns in the data set. Okay, fine. But when it comes to principal component analysis, if you look at if you look at the scatter plot of principal component 1 and 2, sometimes it helps you to identify potential clusters that exist. So one example is, I think, in one of my papers, okay, this one, just a minute. Okay. This paper is very mathematically heavy, so don't, yeah, I just want to explain. Yes. So for instance, if you look at this one, just plotting the principal component 1 and 2 helps me to identify patterns that exist between the data set in a reduced dimensional space. Another example is let me just, so I have a whole code on principal component analysis, just that I was using it to a certain data set, which is like for an actual study that is yet to be published. But I'm just trying to let you see how, yes. So for instance, let's say I have a data set and the data set is on proteins. So it's like a proteomic data set. And we are comparing, and then the data was collected based on some specific materials. And then we wanted to compare whether there's any pattern in the protein expression between those two materials, in this case, plasma and serum. So here it's telling us that the protein expression levels in the plasma material was higher relatively than those in the serum. And that is how beautiful sometimes, or that's how beautiful you can also use principal component analysis to visualize that. So I would say that principal component analysis is multi-purpose. One could automatically use it to aid in variable selection. One could use it to reduce the dimension of the data and include those principal components as predictors in a model. And secondly, or thirdly, one could also use it to visualize patterns that exist in the data. But if you use it as in a regression model, okay, if you use it in a regression model, the beauty is that if I come down here, just a minute. So for instance, I use it as a regression model and included them as predictors, right? But before then, I had to also identify which subset of the predictors I should consider. So it meant that I first of all eliminated all those principal components whose eigenvalues are less than 1. Okay, because if there's less than 1, it means that those variables must be automatically discarded. And the ones that are not discarded, I also applied stepwise regression to select the best subset. So this is what I mean by stepwise regression. So it's like you have a regression model of all your predictors. So in this case, I'm doing it to just the principal component. And then it does, so at each stage, it is now reducing the dimension and it is finding a separate AIC. And then it does that till it gets to the last phase where it tells me that if I should consider a model where these principal components are the predictors, then that will be the best model. Okay. And yeah, so in that case, we went further fine. Going through that process, okay, going through that process helped me to get a model that is, where is it? Just a minute. Help me to get a model that is 81% accurate. And at the same time, so if you use the principal components as predictors, so for instance, these were the best predictors of the principal component, for instance, and you can select which of the protein samples that actually has significant contribution to those principal components you use as predictors, so that it will help you. So it means that if you combine the, how do you call it? If you use PCA to combine the data set, it doesn't throw away the information. As a matter of fact, you'll be able to identify which set of protein samples or which set of variables actually do well or perform better on those principal components that you considered as predictors in the model. So that's just something I wanted you to note. Fine. Okay, so that's all about dimension reduction with principal component. There are other methods. I don't want to go up to that because of time. And for time series analysis is basically where your data is collected over time. Okay, so it means situations where data is collected over time. Sometimes it can just be a single data set. So if you are looking at GDPs, let's say inflation rate over time, that is a typical example of what a time series data. But the moment I decide to collect several time series data sets, like let's say exchange rate data set over time, GDP over time, monetary policy rate over time, let's say inflation rate over time, then I have a multivariate time series data. But the moment this multivariate time series data is collected for different countries, then it becomes a panel data. And that panel data can also be seen as a longitudinal data set. The reason is because longitudinal means you combine a cross-sectional data, cross-sectional because several variables now, and collected over time. Okay, so but that's a typical example of what I mean by a panel data. Yeah, but panel data sets are different from hierarchical data sets. So longitudinal is a more generalization, but remember, like I said, a data can be hierarchical but not longitudinal, and a data can be hierarchical and longitudinal at the same time. Yeah, I think I've explained that. So and the time series models too, we have different versions, and we have machine learning based time series models. Like my paper, the paper I was talking about, I mean, the previous paper on the machine learning. Yeah. So that is just to say that machine learning techniques, we have different methods depending on the kind of data set. Okay, fine. And then there's something that even top statisticians are not aware of. We call it functional data analysis. And functional data analysis is something that most people remember, like even top I mean, I think in my postdoc, I asked my supervisor, like my supervisor in Oxford, that have you heard of functional data? He said, no, this is the first time. Yeah. So it's just to say that many people are not aware of, even top statisticians. So if you don't know, that's not a problem. But functional data analysis is like, it's a new data kind of analysis. Okay. Where for any data set, the cross-sectional data set, the longitudinal data set you'll be hearing. But remember, it is applied to longitudinal data only. So if a data is cross-sectional, you can apply functional data analysis on it. So functional data analysis is a new statistical method where it converts data into curves. By converting data into curves means that it converts data in the real space to something called Hilbert space. In the Hilbert space, data is now converted to curves. So it means that situations where you are trying to look at the rate of change, Maybe there were instances where trying to predict the change in some outcome. Okay, you are looking at the change from baseline, let's say a certain future time from baseline and everything. The beauty about functional data analysis is that if those of us who have done pure mathematics before, or if you've done even elective mathematics at secondary school level, I'm sure at secondary school level you were exposed to differentiation, right? Now you should know by now that the first differential is equivalent to the rate of change. Okay, and if you look at even speed, velocity, and acceleration, if you differentiate distance, you get velocity. If you differentiate velocity, you get acceleration, and so on. Fine. So one thing is that you can convert data into into the. I actually used this method in a competition in the UK. So it was basically a competition organized by Innovate UK. So it's more like the board, it's like the government body that is interested in advancing research and trying to, integrate or somehow help academicians to collaborate with industry. So it means that people from the industry bring their problems, and then we will use our advanced statistical methods to solve those problems within 3 days, and they would take care of as our in terms of how do you call it, where you sleep and everything. So maybe those times I was in Cardiff, and maybe they will be organized. They organized the first one in Cardiff, and the next one I think I went for it in at Manchester University. So it means that you go to a certain university, they cater for your accommodation and everything, your feeding, everything, and the goal is within 3 days apply advanced statistical methods to solve industrial problems. And I use this functional data analysis to make it easier for you to understand this. An application of this was, so there was a big data from the US, and then the data was based on orthopedic surgery. So it's more like orthopedic surgery, and they've collected certain information about the bone at different body location, and they were more like the main outcomes. And then they were trying to now look at certain predictors, how they predict that. But more importantly, they noticed that anytime they treat a patient, okay, like let's say someone is suffering from a bone-related infection, they could treat the patient, and after a certain period of time, it feels as if the patient has recovered in such a way that the values, those performance metric from the data, so it's like there are certain outcomes or primary endpoint that they use to conclude how well the patient is doing. And they notice that those performance metric remains constant. As a matter of fact, it remains constant as if the patient is not suffering from any pain. And then after a certain period of time, there is a relapse, and then the patient suffers for the pain, gets the pain actually relapse again. But the question is, they didn't know how long that remission period is, how long that an individual remains appears to be free from the pains for a period of time. They don't know. How can we learn that based on the population data set? So what I did, and it was a smart thing I did, and ever since I developed a good relationship with the team, and I'm even one of the data scientists for that company. And was that I used the functional data analysis to do that. And the first thing I did was I converted the data set into curves. And the data set is a longitudinal data set. So converting it to curves means that I've converted it from the Rel space to Hilbert space. And after doing that, now in the curves, the data now is like a function. So just imagine if you consider a particular individual data over time, you've converted that data into a function that is differentiable. So it means if I want to know the rate of change, I can differentiate that data, and the first derivative is like the rate of change. And imagine if you now plot the rate of change across all the patients, and then you notice that there's a certain period where the rate of change was zero. You know, when the rate of change is zero, it means that that data was not changing over time. So it means that I was able to get a visualization such that the data was changing, and it got to a certain point, the rate of change was zero up to a certain point, and then the rate of change, and then the rate of change was non-zero anymore. So I was able to know exactly for how long the rate of change remains zero. And by so doing, I was able to tell how long an individual can undergo remission. That is, feel like they are free of or have recovered from the pains, and how long it takes. I was able to tell that from the functional data analysis. So it's just a simple application of the functional data analysis. And there's another one called network analysis. Network analysis is very important. And there are different types of network analysis. Even those in political science, you have there's a certain network analysis, the analysis called the discourse network analysis or something. And it's also used by those in political science to check how different opinions of politicians agree with each other. And there are other performance of agreement or metric of agreement. So we have intra-class correlation, we have kappa statistics also there. But the network analysis is just a way to visualize relationship between, let's say, certain outcomes of interest in the graphical structure. Okay, so one example, one perfect way where I applied network analysis was during my MPhil. So my MPhil research, I did it in Ghana, which was predicting. It was using something called Markov chain modeling of HIV, tuberculosis, hepatitis B transmission. In 2018, it won the best research in Ghana at the master's level. And so let me see. Okay, this is one of the publications from it. And so from here, let's see how network analysis was employed. Okay, so let me just download this one. Okay, all right. So for instance, we know that if so I was looking at HIV, tuberculosis, hepatitis B. So there were two publications from the paper. The work was like MPhil, but was done like a PhD, such that when you go to Google Scholar and you type the research work, it's treated as a PhD work. If you go to Google Scholar and you type the topic Markov chain modeling of HIV, tuberculosis, hepatitis B, yeah, it's treated like as if it was a PhD work. Fine. So where's the PDF? Just a minute. Okay, yeah. So just a minute. So here, so for instance, one way of applying network model is so for instance, HIV, tuberculosis, hepatitis B. We do believe that if an individual is suffering from HIV, one of the first tests they do is to check whether the individual has tuberculosis. Because for every 4 individuals with HIV, we believe that one of them has tuberculosis. So it means if someone is suffering from tuberculosis, there's a chance that that person could have HIV. It's not always the case. But we are just trying to say that HIV, the leading cause of death among HIV patients is tuberculosis. So it means there's some kind of link or association between HIV prevalence and tuberculosis incidence, right? But we didn't know whether there's relationship between HIV and hepatitis B or hepatitis B and tuberculosis. We didn't know. And remember, for HIV, it's not really an infection necessarily. What HIV does is that after your immune system is compromised, it allows other infection called opportunistic infection to fight for or compete for the health of that individual. So it means it destroys your immune system such that several other diseases can now occur in that individual, right? But we didn't know whether hepatitis B was one of them. And we didn't know whether if an individual has HIV, there's a chance that the person could suffer from hepatitis B. So one of the ways for me to visualize that was to use something called Bayesian network or directed acyclic graphs. So this one means like I used a network analysis to check whether there is going to be a relationship between them. You can see that there's a relationship from HIV to tuberculosis. There's no arrow joining hepatitis B to HIV or hepatitis B to TB. It is only joining HIV to TB. This is and then you notice that it is coming from HIV, not TB towards HIV. So this is to say that we are not saying that people with HIV would have people with tuberculosis will have a high chance of HIV. We are rather saying that those with HIV, there's a high chance that they will have tuberculosis. Okay, so this is just to say that we can use network analysis to visualize complex associations in a graphical fashion, okay, or in a network fashion. So in that case, there's something called nodes, okay, and then relationship associations are represented by those arrows, and the arrows are called edges. Okay, fine. And there are so many models, and time might not permit us. But the only thing maybe I'll talk about now is the robust regression methods. I've already talked about lasso, ridge, and elastic net, right? You can use them as a regression, and you can also use them for variable selection. As I said, ridge is not the best for variable selection because, like I said, it sets variables of low importance to a weight of something close to 0, but not 0. The lasso is a bit brutal, and it means that if you want to now know the best subset of most influential predictors, okay, whilst eliminating all those that are not important, then lasso becomes the alternative. But there's something called quantile regression. I think I'll just talk about this and end for the first phase. Yeah, I'm sure everyone is tired by now. Now, quantile regression, many people probably might not be familiar with, and many people don't know that most of their research that they've been doing, they actually need to use quantile regression, just that they didn't know. So all the GLMs, the generalized linear mixed models, the generalized linear models that we've been talking about, remember they predict the expected values or the mean of the data. They predict the means. And if you have probably been in an elementary statistics class, you notice that whenever there are outliers is where we have extremely large or extremely small data, okay, or values in the data. And statistically, an outlier is situations where, let's say if you pick a variable, you find a mean, and then you find a standard deviation. Then you construct this range. The mean minus 3 times the standard deviation as the lower limit, and then the mean plus 3 times the standard deviation as the upper limit. That range, okay, is one way of concluding whether any data point is an outlier or not. Any data point that falls within that range is not an outlier, but any data point that falls outside that range is an outlier. And if it falls outside that standard deviation, what we mean is that any data point that falls outside 3 standard deviations of the mean is an outlier. So that's the statistical definition of an outlier. But remember that outliers, there are two things that will not make a data to be normally distributed. So mostly when the data is not normally distributed, we conclude that because they are outliers. It's not always the case. A data can be free from outliers. So like I said, the range 3 times the standard deviation minus the standard deviation minus 3 times the standard deviation. Oh, sorry. The mean minus 3 times the standard deviation as the lower limit, and the mean plus 3 times standard deviation as the upper limit in order to define an outlier. There are instances where bulk of the data falls 3 standard deviations above the mean. That is right skewed. And there are instances where bulk of the data set falls 3 standard deviations below the mean. That is left skewed, even though they are still within the range. So this is to say that a data can be either positively or negatively skewed, but has no outliers. And when a data, so it means that there are 2 sources of non-normality. A data can be non-normal, not because of only outliers, but because of skewness. But remember that when a data is non-normal because of outliers, the certain data transformation like logarithmic transformation can maybe convert the data to be normally distributed. But when the non-normality is due to skewness, whether left skewed or right skewed, no amount of transformation will convert the data to be normally distributed. So that's one thing I wanted you to note. Fine. And we are saying that all the regression models are used to predict the means, okay? But situation, and it means that there are certain parametric assumptions. And mostly when the dependent variable is normally distributed, it kind of helps you to get a good fit. Although it's not really a requirement. It's not really a parametric assumption. Most of the parametric assumptions are about the regression residuals or the error term, that the error term must be normally distributed and so on, but not necessarily dependent variable. But if the dependent variable is normally distributed, it helps. The reason because the dependent variable is expressed as a function of the error term. So it means that technically If the error term is normally distributed, any linear function of a normal distribution should be normal distributed. So this is to say that if the dependent variable is normal distributed, it kind of helps you it helps you for the residuals to sometimes satisfy the parametric assumptions of normality. But that is not always the case. So situations where even after data transformation, you still didn't achieve normal distributed residuals, okay? And somehow the regression estimate or the regression, even the R square is very low, or let's say the model is poor fit. It's just because the data is non-normal distributed. Let's say the data is, especially data set from immune responses, okay? Those who are into proteomics or genomics and so on, most of the data set are often skewed. And whenever they are skewed, sometimes no amount of transformation makes the data to be normally distributed. Now look at something. If a data is not normally distributed, but after taking log transformation and the data becomes normally distributed, it means that that data is log normally distributed. It's just something I wanted you to note. So but a data can be normally distributed and its log transform also normally distributed. And the data can be non-normal, but certain transformation can cause the data to be normally distributed. In the case of a log, if log transformation results in a normal distributed data, that data set, the original data set, is rather non-normally distributed, log normally distributed. Fine. Now, quantile regression rather helps us to estimate specific quantiles of the data, not the mean. So it means means are estimated based on the classical regression models we've been talking about. That is why whenever you are talking about interpreting the regression estimate coefficient for a dependent predictor, you say that a unit increase in that predictor would cause the dependent dependent variable, if it is continuous, the expected value to increase by something. So you see, the expected value means the mean of the data to increase by a certain amount based on the regression coefficient. If increase if it is positive and decrease if it is negative, fine. But when it comes to quantile regression, it helps you to rather consider predicting the median of the data if you set the quantile to be 50% or 0.5. And you can also use it to look at factors predicting the 25th percentile of the data. You can use it to predict factors predicting the 75th percentile of the data. And mostly those who do clinical trials or those who are doing studies where the data is heavily not normally distributed and all the classical regressions are failing. Okay, and since they are failing, you don't want to predict the means, you want to predict the medians or other quantiles. And because you know median is less affected by outliers, so predicting the median would be what advisable in that case. And that is why when you are doing classical hypothesis testing, even when the data is not normally distributed, and that you cannot use the parametric hypothesis testing, you are then forced to now use the non-parametric test. Right. So for instance, for independent test, the non-parametric version is Mann-Whitney test. And then for the ANOVA, the non-parametric test is Kruskal-Wallis. For repeated measures ANOVA, the non-parametric test is Fredman's test. All the non-parametric tests, they rather kind of test the median, not the means. Okay, fine. So quantile regression is just a way of predicting specific quantiles of the data, whether the median, whether the 25th percentile. You can even use it to look at factors predicting the maximum of that data, especially those who do extreme value analysis. You can actually use quantile regression to look at predicting factors, because remember, with the regression, you are looking at factors predicting the averages. So it means you can use quantile regression to look at factors predicting the medians or factors predicting specific quantiles, the 25th percentile, the 75th percentile, even factors predicting the maximum value of the data or the minimum value of the data. You can use quantile regression for that. So that's the beauty, and it's much robust to departures from parametric assumptions. So that's just something I wanted you to note. For the spatial statistics, mostly those who are into geography, ecology, they make use of that, especially when they are interested in spatial distribution. Sometimes if you're looking at the spread of an infection over some geographic locations and so on, then that kind of analysis you can use. So those geostatistics is where you see the statistical analysis and there's a map with some specific summary measures inside the map and all those kind of things. That's like the spatial statistics. And the Bayesian statistical methods, I don't want to talk much about it, but the only take-home message is that the Bayesian is not a statistical model. It is just a method of estimation. all the classical statistical methods or all the classical methods I've mentioned, most of the time, the parameter estimation is done either by method of least squares, method of movement, or mostly by maximum likelihood. That is if we know the likelihood function. But Bayesian, and then so it means the frequentist way of estimating parameters assumes that the parameters are constant. But Bayesian assumes that the parameters we want to estimate are random variables. And because they are random variables, it means that we can get distributions of that parameter. And by getting distribution of that parameter, it means we can learn more about the data. So Bayesian statistical methods allows us to use certain prior information about the parameters. Okay, certain prior information, existing information in the literature to improve our parameter estimation. So you use the existing information about the parameters in the literature. If you don't know any existing information and you still want to use Bayesian, we use something called non-informative priors, and combining that with something called the likelihood function. The likelihood function is just the probability distribution of the data. And then based on that likelihood function and the prior, it produces something called posterior distribution. Now, when you get the posterior distribution, the average of the posterior distribution is just the parameter estimate. So it means Bayesian statistical methods are basically, the statistical methods here are all the statistical methods you are aware of. Just that if the method of estimation applies Bayesian estimation technique, then it gives a different name to it. But remember that not all that, the only instance you can use classical Bayesian approach is when you know the exact likelihood function. So it means anytime you can implement maximum likelihood, you can implement Bayesian approach, the classical Bayesian. But there are instances you cannot evaluate, or the likelihood function is mathematically intractable or computationally expensive to evaluate, or you can't even write down the closed form, and it introduced something called approximate Bayesian computation. So in one of my papers here, this particular paper, you'll be exposed to a certain method of estimation called approximate. It's called approximate Bayesian computation, which is used in doing instances where the likelihood function is either mathematically intractable or computationally expensive. So I'll end here with the first session. The last session, remember, is just going to be 10 minutes and I'm done. So at this point, if you have any question, I think I should take a question now because people are tired. So do you want to ask me some specific questions if you have, and then we would proceed? Because we've spent a huge amount of time already, I'll just spend the last, because we started at 11, right? So we've literally spent 2 hours on just this. So what that means, I'm just going to spend 10 minutes, just 10 minutes on the last part, and then we are done. So should I continue the last part in 10 minutes before taking the questions, or I should take questions now?
No.
Okay. Should I finish first and take the questions?
Yeah, I would
No,
suggest
you have to take some water. You are tired.
Yeah, I'm actually tired, but it's fine.
No, take some water first so that we mobilize our small questions, then we give to you.
Okay.
Uh-huh.
Oh gosh. Anyway, teaching is not easy.
Yes. President, please, can I speak?
Oh, yeah, sure. You have the floor.
Okay, all right. Thank you very much. Dr. Chumesi, thank you for the introduction. Honestly, you've done a great job. In fact, you taught me at the University of Ghana, Legon. So when I saw the notice, I was so much happy. But just that you left very soon in 2018 for your PhD. So I remember you a lot. So please, I want to say that, hello, can you hear me?
Yes, I can hear you.
You can hear you.
Oh,
We can hear you.
Okay,
Flow.
I think you have said a lot and you've made meaningful, give us a lot of information. Especially, I was so happy about the functional data analysis. It's my first time too, so I will do more research on it and also follow your YouTube page and then learn a lot. I would like to know when we are going to have the practical section, and then we'll take it from there. Thank you. That's my.
No problem. Yes, that for the podcast session, I time couldn't permit me. So the only good aspect is I'll just talk about what I did, and then I'll give everyone an assignment. An assignment means that you are going to learn how to do survival analysis, the classical one, and also the multi-state Markov modeling. Situations where you want to now account for the possible transitions that occurs before death eventually occurs. Like I think I've explained that already. Yeah, so I couldn't generate all the codes because I was really pressed with time, and that's why I joined very late. I thought I could make it possible, but I couldn't. But that's fine. So yeah, so now so the question is, should I take questions now or I should finish?
I think others have some few questions that they can ask. So thank you very much.
Okay, they should go ahead.
We have some questions in the chat box.
Okay. People, could they talk? Is it possible for them to ask it?
All right.
So that I don't miss anyone. So those who send their question, is it possible? Okay, so someone, okay, what else? If they could talk out, that would be great. Okay, Isaac, can you go ahead? Yeah.
Yeah. Thank you very much, Doctor, for your information. I'm just looking at a possibility of constructing a biogeochemical model from compost use in cocoa farms. And I wanted to find out if there is a package in how that I can follow on, or I have to write my own functions to do the construction.
No. Now, I think on my YouTube channel, there's even a video on how to use ChatGPT to aid in programming. Now, at first, I keep telling people that during our time when we were doing our PhDs, if ChatGPT was in existence, some of us would have finished our PhDs within a year because there was no ChatGPT. Like, for instance, when it comes to disease modeling, I had to get my disease modeling training in Cambridge. But that training, if there was ChatGPT, I wouldn't have needed it. Okay, so I'm just trying to say that now ChatGPT can be used to do anything. So whatever you want to do, when you go to ChatGPT, don't let those in the social sciences who are demotivating people from using ChatGPT to because there are people who are they have phobia when it comes to giving data or numbers. So when they hear anything about ChatGPT for programming and stuff, they seem to be a bit worried and scared and no. But the truth is, it's a machine. You just have to know how to use it. If I give you a car, you don't know how to drive it, you are going to get an accident. Not because the car had a problem. It's just because you didn't know how to use it. So it means for ChatGPT, for instance, what you just described, all you need to do is that go to ChatGPT, tell it that you have a research problem you want to do. I'm not just telling only the person who has the question, all of you. Just go to ChatGPT, tell it whatever you're trying to do, give it a background information that, okay, you want to do a study on so and so. Even when you don't know the kind of methods you want to do, then you say that based on these background information, suggest possible methods that I can use to analyze that kind of data. You can describe the data structure, everything, just provide it with adequate amount of information. The more information, the better, or the best way to get a more tailored response. So it means that if you wanted to give you a very accurate response, it will be dependent on the amount of information you give it. And then you can tell it to now implement the suggestions in R, and it can generate all the codes for you. And then sometimes there might be some of the codes might not be implementable because there wasn't a data. It just gave you like more like a skeleton. You can even tell it to simulate the data and implement it so that you can run the codes. And anytime you run the codes and you get an error, just copy the error message. Don't even tell anything. Just copy the error message and paste it in that same session of the ChatGPT. And then it will try and correct the error. If you now do the corrected version, you're still getting error, copy and paste the error. It will keep improving it till it gets the right answer. That is why it's called artificial intelligence. It keeps learning. It keeps learning based on So your answer can actually be solved in ChatGPT, and that's the best way you should do. I don't want to give you some, but the whole point is there must certainly be packages for that. And if you want to even know the kind of packages, you can ask ChatGPT to do that. Before even ChatGPT, you can also Google. But ChatGPT, I think, would it helps you not just about if you are developing, let's say, research proposal. The only thing I would advise people not to do is don't use ChatGPT to produce an essay, or let's say you are doing literature review. You use ChatGPT to produce an essay and all those things, and then you just copy and paste that into maybe your Word document. That will be AI. There will be AI detection. There are softwares to detect AI, right? But if you go to my YouTube, there's a whole application called Quillbot. It is used for paraphrasing. And those who get the premium version of Quillbot, you can use it just like Grammarly. Quillbot can be used for paraphrasing. Let me. I've explained it before, so I didn't want to. Yeah, so Quillbot can be used for paraphrasing. It can be used for improving your grammar. It can be used to check for AI detection. And if you have Grammarly, you can use Grammarly to check for also plagiarism, right? And Quillbot also allows you to check for that. So, but Grammarly is only for more like grammar correction. I think Grammarly is the best if you want your English to be straightforward. Grammarly kind of makes the English quite straightforward and professional. But Quillbot can also be used for that. Yeah, so that's also something you should know. So just don't. But when it comes to programming, there's nothing like plagiarism when it comes to programming. All right, Bernard, do you want to ask your question?
Yeah, no, thank you. But I have a second one with this person. Do you do a one-on-one consultation?
Not really. It's because I'm quite busy. Apart from my current role, I also do. I'm part of I also do online teaching stuff. So where we teach university level, how do you call it? University level stuff. It could be GRE, those professional exams and all those things. So I do those things part-time. But I don't do one-on-one, otherwise I'll break down because my role is demanding. Even doing YouTube alone is also demanding. Doing these kind of programs for students is also demanding. So the moment I say, oh, everyone can just contact anytime, I think I'll break down. So that's why I decided to create a YouTube channel. So that anytime we do these things, we put it there. Then if anyone wants specific information, you go there for it. Yeah. So I don't do one-on-one consultation. And with the help of ChatGPT, you don't need me. That's what I'm trying to say.
Oh,
With ChatGPT, you don't even need a supervisor, but you use a supervisor as just a formality. And trust me, make good use of it for those who are doing your PhDs, your masters, and so on. Yeah.
Yeah. Thank you very much.
No.
Okay. Doc, I'm back again.
Okay.
Sorry. Thank you very much. I would like to ask whether you've done a video on the construction framework. We're using R, whether you've done a video like that. If not, then I will recommend that you do it. Maybe you add it to one of your schedule plan, how to program so that it does a simple construction framework as you've shown to us.
Oh, okay,
Yes.
okay. Yeah, I mean, for the frameworks, let me see. Let me share my screen. Okay, so for the frameworks, the truth is that you can use it to do complex stuff. So, what's this study on those findings? Okay, this one. Let me just come down. This one looks a bit small, but fine. Yeah, so I'm just trying to say you can use it for any conceptual framework, and I think I will try and consider that as you said. No worries.
Yes, Doc. I want you to maybe a video as you have been doing, like a video on that, so that you post it. Then you can follow through with that.
No problem.
Okay. All right. Thank you.
Okay, so should I just wrap up within 10 minutes and then I can take questions afterwards?
Yes.
Okay. Yeah, because there's no time, I'm just going to wrap up in 10 minutes, and I'll direct students to specific links. Fine. And remember, there are so many online, like, that's the interesting thing. Now, learning is supposed to be easier than it used to be. There are so many online information. Sorry. There are so many online information on how to do anything in, let's say, R online. So personally, I keep telling students from my first YouTube video, I'll tell you that once you are able to import data, not just in R, even when you want to do SPSS, when you want to do Stata, when you want to do SAS, Python, once you know how to import a data into a software, the rest is just making use of the internet. Because when it comes to the programming languages, packages are only installed when you need to use a certain function, a customized function created by someone else. Okay. And when you go to a block, so for instance, let's say you want to do multi-state Markov modeling, there is a whole link on this. I think the beauty is that this is the kind of the experiment I wanted us to do. I'll add the link to it so that you can follow through the codes. Okay. So that you can follow through the codes. Yeah. I couldn't get time to develop all the codes. So I'll just add this link when you get to the multi-state bit so that you do it. And then for the classical survival analysis, so I'll just add a link to it. I'm just trying to say that there are links to everything. So let's say you went online, you saw this blog, and you've seen these things, library. The moment you see library, it means whatever is inside that library is a package you need to install in order to be able to follow through everything they've specified down there. Okay. So that's one thing you should note, right? And anytime you are installing, they should be in parentheses. Okay. But when you are loading with a library, you can choose to bring the quotations or not. But if you are installing, you should bring the quotations. Okay. If you don't bring the quotations, it will come as an error. But if you are loading, but when you install only once and you don't have to install ever again. So that is why after I installed, I bring this hashtag. Hashtag means that it should treat now everything after the hashtag like a comment. Okay, or it means it shouldn't run if I run that function. It shouldn't run as a yeah. So the hashtag is just a way of commenting out or adding specific comment or whatever. If you don't add, so for instance, if I want to write my name Clement, if I run this, it tells me it's an error. But the moment I bring an hashtag and I do this, it's not an error anymore. Fine. And all the codes in the Jupyter notebook, remember, you can just copy and paste into R. And as a matter of fact, I've demonstrated how you can download it just as if you've done it in RStudio. Okay, but it helps, especially those who are doing their PhDs, when you want to. As a matter of fact, you can clearly see you can use it for presentation. So it means that you don't necessarily, yeah. So here, the next phase of the program outline was, okay, that's fine. So this one is multi-state. Yeah. So the next phase of the program outline was just to talk a bit about what is statistical programming or mathematical programming and what is IDEs and so on. Yeah. So remember that programming is very broad. Like, it's very broad. Just like even through going through what you've just learned today, you've noticed that. Please, can you see my screen?
Yes, we can.
Yes.
Okay.
Yes. No.
Okay. Just going through today's session, you've noticed that even when it comes to data, we have different data structures. We have different areas of application and so on and so forth. This is to say, when it comes to programming, there are a group of people, especially computer scientists, who actually employs programming the same way statisticians or mathematicians also do. But one thing you should notice that those who are most programmers, or those from there are people from computer science and other people not from computer science whose programming expertise is just to develop applications. So developing applications, programming to develop applications is different from statistical programming to analyze data. So it means that never confuse yourself. When, let's say, you wanted to learn Python, and then you hear that someone is very good in Python, the first thing you need to ask is, what is the area of application? because someone can be good in Python for developing games or applications, but a person might not be good in Python for statistical analysis. And as I've already said, the knowledge of programming, especially when it comes to statistical analysis, it complements, you have to add your statistical knowledge. So it means that when you are using the software, it's not the software that is telling you what to do. You should know exactly what you want to do. You should know that, oh, okay, for this data, I need to use ANOVA for this hypothesis testing because I have a continuous outcome and I'm comparing between 3 or more groups. But before that, I need to test for normality. If the data is not normally distributed, then I'm going to use a Kruskal-Wallis test, which is a non-parametric version to compare medians, right? Fine. So in that case, it means I'm going into the software, doing what I need to do. The software will not automatically tell you what to do. So I think one of the mistakes was back in Ghana, people thought I was so good in programming, but little did I know that I was making use of only packages. So if you use someone's package to perform an analysis, remember that if there's a package for something, don't create your own. You only create your own if the existing package cannot be adapted or adopted for what you are trying to do, or there's no existing function or package for what you are trying to do. Otherwise, there's no need to create your own function. Fine. But you notice that those who are doing lots of elementary stuff, most of the time, they are existing packages. But if you look at, for instance, this particular paper, which is published in the Bulletin of Mathematical Biology, it is actually the top journal for the Society of Mathematical Biology. So it means for mathematical biology in the world, for their society, that's their journal. So it's quite a heavy journal. But with this particular journal, so you notice that everything you see in this particular publication, right from, so I'm developing a stochastic simulation model, right from the stochastic simulation model, the algorithms you will see here, let me just come there, all these mathematics and everything, including the algorithms you are seeing here, there's no package for it. So I have to develop my own codes to achieve that. Okay, I have to develop my own codes to achieve everything you are seeing there. So in that case, that is one of the instances where if you don't know how to create your own functions, it becomes a problem. Okay, fine. So it's just to say that statistical programming, you cannot do statistical analysis in a programming software without knowing the right statistical methods to use. So don't just talk about, oh, I want to know. Okay, so you meet someone, the person says, oh, I have been programming in R. Then oh, can you do this data analysis for me, or can you tell me how to fit a certain model? Remember, the mere fact that someone has used R for something else doesn't mean that they can use the same R for another thing. I'm just trying to say that the knowledge or whatever you want to do in R is dependent on your knowledge about the method you want to use. If you don't have the knowledge, make use of online resources. ChatGPT, make use of online resources. How to do this? Okay, so for instance, if you want to fit a logistic model, just go to Google, type how to fit a logistic model, a logistic regression in R. So for instance, if I type how to fit a logistic regression in R. So the most important thing is know how to import data, and that's all. You see, there are so many blocks. This block, how to perform logistic in R, how to perform this, different blocks, and they are free online. So I just have to click on one of them and check which one is much more useful for me, and so on. And by the time you realize, you've also, I mean, yeah, I'm not even happy with this one, but I mean, then I'll go to the next one. Okay, this one is trying to explain stuff, and this one is doing stuff. Okay, this has fitted a model. And if I want to look at interpretation, it's even going through other models. I mean, it's doing other goodness of first statistics, variable importance, it has done that, and so on and so forth, and trying to make predictions, and so on and so forth. Yeah. So in that case, it means just using this, once I'm able to import, it always starts with the data. So it always starts with a certain data. So once you replace this data with your data, then it means you should be able to adopt every other thing it's used. And remember, most of the time we split the data into training and testing, and then we use the training to fit the model, and we cross-validate the model based on the testing set. I think I've already done that on the YouTube channel. A typical example of that is on the YouTube channel where we are, yeah, this one. So building and validating a predictive model cross-validation and accuracy. It was a logistic, it was using statistics to aid in forensic research. You can just watch that and you enjoy. Please don't forget to subscribe. Usually, most of my subscribers are not even Ghanaians, and it's quite unfortunate. Yeah, and because sometimes Ghanaians, we need help, but we don't want to support. For me, the only support I can get is your subscription. So please don't forget to subscribe so that and you don't miss future, how do you call it, future uploads. Fine. So that is what I wanted you to note about statistical programming, that understand the theory or just know the theory. You don't need to understand the mathematics. Just understand when to use this method, just like I've done today. Just understand when to use a particular method. Once you know when to use it, then you now search for how to do that in the software, online or in ChatGPT. Okay, so that's all I wanted to know. Okay, so the next thing on the list is, what is an integrated development environment? I've already talked about that on my channel, but basically integrated development environment is basically called, the ID is integrated development environment. It's just a platform that we use to run programming softwares. So SPSS, for instance, it is an IDE to run SPSS. Stata Studio is an IDE to run Stata. So for R, we have R Studio. It is an IDE to run R. Jupyter Notebook, it is an IDE to run more than 30 programming languages. So at the moment, I have only R and Jupyter kernel that I'm using here. And that means I can run R, and I can actually open Python and be running it alongside. And the beauty about Jupyter Notebook as an IDE, as you can see, once you have your code, the output is just underneath it. And the graphs you produce, you don't have to save them separately. You don't have to save them separately. If you now get access to the, how do you call it? If you get access to the, if you download it as an HTML file, just as we've downloaded it in my downloads, if I open on it and I want to save a particular graph, let's say I want to save this which graph? Let's say I want to save this graph. I just have to right click and click save as the normal way and go and save it as a particular folder. And it will keep the resolution. And the beauty about R is that you can set your resolution. So for instance, if you look at this one, I've set my resolution to be 300 dpi. So this is to say, especially if you are publishing, you notice that most journals says that your resolution, your figures resolution should be at least 300 dpi. Okay, 300 dpi. And that 300 dpi is basically what I've just done here. Someone will say, why don't I make it 500? Remember that too much of everything is bad. So someone will say, oh, if I want my graphics to be the best, why don't I set it to 500? The more you set the resolution, then it becomes too good. By too good means it also becomes bad. But 300 is like the best standard that you can ever use. So all my publications, I set it to 300. Okay, so so that's basically one of the fine. So it means that Jupyter Notebook, I would say, is the best IDE you should use, whether you are doing Python programming, C+ programming, or whatever you are doing. And RStudio can be used for now. So all the codes you can copy and paste in RStudio. And like I just showed you that I can also download it as an executable script. And the executable script is similar to download it as an RStudio script. And that's what I did earlier. So like the whole course, I've downloaded it as an RStudio script. But you notice that in the script, I don't see, this is where I see the codes, but I don't see any graphs. I don't see anything. So if I send you this, you might not know, first of all, whether there's an error in my code, or you might not even know whether what this output, this one, if I run, will give me. Okay, so that's the whole point. But if you should run it from scratch, of course, you'll see the graphics under this session. And just watching the first YouTube video, you know how to use RStudio and how to install it. You know how to use RStudio, and then and so on. Fine. Okay, so back to yeah. So here the next thing is, I just wanted you to note that there are instances where previously you've been doing your analysis in SPSS. But because you've come for this session and you've noticed how useful R is, one of the advantages of R is that there are certain complex statistical analysis that SPSS, Stata, and probably SAS cannot do. eViews, Minitab, those who use eViews, Minitab, Gretel, even GraphPad, Prism, all these statistical softwares, okay, Tableau and the rest, all those statistical softwares, what I'm trying to say is that there are certain advanced statistical methods that they cannot do. It is recently that SPSS is now having certain capabilities to do machine learning, but that one is in the newest version. Okay, I have the newest version on my Mac. That's the only instance. Another question someone will ask is it good to run R on a Linux machine or a Windows machine? The only difference is that for Linux machine, there are instances where you are doing complex simulations, and the simulations will involve, let's say, 100,000 iterations, sometimes 1 million iterations, and so on. Where each iteration, let's say, each iteration is like a simulated data. Let's say if each simulated data is taking, let's say, 10 minutes, and you are doing 100 million, or you are doing 1 million, it means that it could take you sometimes about 7 days to get an output. Most of the time, when you run a code in R at this stage, within seconds, you get your output. But I just want you to know that a time is coming. So, for instance, this particular paper I was telling you about, okay, this particular paper. For these simulations, you are seeing them there like that. The truth is that it takes so much time. But if you can minimize or cut the time, if it is 7 days, you can reduce this to 5 hours. And how do you do that? We call it doing paracomputing. So paracomputing, remember that anytime you run any code in R, it is running on only one processor. Even if your computer has 7 processors, it's running on, for instance, my MacBook has 12 processors. Anytime I run this, it runs on just one processor. But if I'm doing, let's say, 4 loops or looping, and each loop each iteration takes a lot of time, and I'm doing 100,000, 10,000, 1 million iterations, then you should be able to parallelize your codes. By parallelizing your codes means that you are setting the code in such a way that if there are 1 million, let's say 1,000 is running on a particular core, another 1,000 is running on another core, another 1,000 is running on a different core, and the performance on one core should not affect this performance on the other core. Meaning that if you do paracomputing, and your codes are running in parallel, it means that the speed or the performance of on one particular core does not affect the other. But if you didn't parallelize your codes, what it means is that you have to wait for one of them to finish before you go to the next, about 100,000 times or 1 million times, depending on if those who do a lot of Monte Carlo simulations or those who do stochastic modeling and it's quite mathematical heavy. You now do paracomputing so that your computer, your looping would run on multiple cores to speed up the computational time. Okay, so that's what I wanted you to note. But in doing the paracomputing, it is easy to do that on MacBook or Linux machines than on Windows. Windows use something you call on MacBook, the function we use to do the looping is called MCL apply. That is on MacBook or Linux machines. And that one, when you are doing it on Windows, that function can only work when you set the number of cores to 1. But there's a certain package called PAR-L apply. That is also for a certain function called PAR-L apply. That is also for paracomputing on Windows, but that one, it takes a lot of time. And to set it up it's not straightforward. You have to define many things, but on Linux it's straightforward. And another thing is that graphics on Windows, on Linux is much more beautiful than Windows. So always Windows graphics, MacBook or Linux machines, our output, the graphics, the resolution are quite clear. But on Windows, sometimes it looks a bit blurry. Although it's okay, it looks a bit blurry. So sometimes maybe the best thing is to export the data as a PDF. And there are ways to do that. You can just make use of ChatGPT, how to export a data from R as a PDF, and you should be able to do that. Fine, but that might preserve. PDF preserve data quality, or it preserves, how do you call it, the structure of the data. It's protected document format, so it protects it. So you can actually export it as a PDF, even if you are doing it in RStudio. RStudio, the graphics are sometimes terrible. You can export your graphs as PDF, and in the PDF format, you can always convert it to PNG or other format. Fine. So here we are just learning how to import different data structures. So imagine if you've been doing your analysis in Stata. Now you want to replicate the analysis you did in Stata in R. Or let's say you use Stata to do some time series analysis. You were doing some granular causality test, something, and then you were told that you are supposed to do a nonlinear granular causality test, and Stata cannot do that. And you want to do that in R. What I'm trying to say is that you can import that Stata data directly into R and use R to do that. Let's say your data was in SAS, and you want to change the SAS data to Excel, or you want to change the SAS data to Stata, or you want to change the SAS data to SPSS, or you want to change any data format to another data format. You can also do that. Now let's see. So for instance, this is there are packages you need to install. Okay, you install by using this, taking away the hashtag, but you only install a package once. Okay, once you install, and remember, you need an internet to install a package. Fine, but after installing a package, you don't need to install it ever again on your system. Fine. So here is a simple, but before then, there's something you call setting the working directory. There are many ways to import the data into R, but the easiest of them all is set a working directory. Direct working directory is that I created a setting folder called NUGS-CHINA on my desktop, and I just went to copy the path. I just went to copy the path and copy it and paste it. But the take-home message is that those of you who use Windows, if you use Windows, this is how your path would always look like. It will look like a C and whatever, but it will be going this way. And then you see users, it will be going this way. Okay, like that. It will be two bars, and it will be going in the so it means this is like backslash. Okay, so those who use Windows, that's how yours will look like. It will look like that. Like that. But those who use MacBook, it will be automatically in the /. You need it in the / to set a working directory. So those who are using Windows, once you copy your path, you just need to change it into the /. Okay, but those who are using MacBook, is straightforward. And if you want to know the path, I think those who use Windows is so easy. But those who use MacBook, I just go to my desktop. I look for the folder that this folder called NUGS-CHINA. Can you see my desktop?
Yes.
Hello. Okay. Yeah, so I look for this. Okay. So I look for this folder called NUGS-CHINA. Any data that I want to import in R, I have to put it there. So you see, I have SPS data here. I have SAS data. I have Stata data. I have Excel data. I have CSV data. All the data that I want to import, I have to put it in that folder. And that folder, the path to it is called working directory. Those of us who use Mac, you can go to get info and copy. If you're a Mac user, I'm sure you know how to do that. And those who use Windows, mostly you know there's a bar, there's something up here that when you click, you're able to see the address directly. Just copy that address and go and paste it. Go to your R and paste. Just that when you paste it, you have to change all the backslash to /. Okay, before it will work. Fine. So once you set the working directory, then to import data in CSV, you don't need a package to import a CSV data. That is why if a data is in Excel, it is better to convert it to CSV before you use. And to convert it to CSV, if I should open, let's say this is an Excel data. Let me open. So this is an Excel data. If I want to save it as a CSV, I think I've done all these even in the first YouTube channel video. You just go to File, you go to Save As, just like we're saving it for the first time. Then you go to the file format. and then you choose CSV, delimited. Those who use Windows, you should be careful. There are many delimited. Even on MacBook, you see, we have delimited values. You are looking for delimited without anything. This one, those who use MacBook, and those who use Windows, you have delimited Macintosh, you have delimited with different wordings to it. All you are looking for is delimited without anything. And that is what you need. Okay, so don't forget. So that is how easy. And when you save it as a CSV, sometimes you get some message that you are going to lose certain things. No, don't worry, nothing is lost. Okay, fine. All right. So, but yeah, so it means that if you are importing a CSV data, you don't need a package. But if you're importing Excel, you need a package. So why would I need a package if I can just convert the Excel data to CSV manually, simple, and just import it without a package? Fine. But this is how easy to import. It is the name, exactly how you name the CSV data, and you bring the CSV, and that is all you need to do. And there was a data called transformed data in that's what I opened, this transform. All I need to do is to copy the name and go and paste. Okay. The moment then you get the spellings wrong, you get an error, right? So go and copy the name directly and paste. And don't forget the extension. And then if I want to import SPSS data, this is read.csv. The package is the Haven package. The Haven package is used for that. And then I just have to specify the name of the SPSS data. And now I have managed to import an SPSS data into R. Okay. Now let's imagine you wanted to save the SPS data as Excel or as CSV or as data or as any format. Now just imagine I have imported a Stata data. This data is the DTA, is a Stata data. After importing, I am exporting it as a CSV back into my repository. So you see, the moment I run this ADP underscore Excel, right? This one, I've converted the Stata data to CSV, okay? CSV is an Excel format, just that is an Excel. So, and that data is this one. I literally just converted it to. So it means that situations where you have data in Excel, you have data in SPSS, and you want to now change the data structure or the data from SPSS or Stata to Excel, you can easily import it into R first and export it in any version you want. Okay, that is how easy it is. So that's all I wanted you to note. I mean, traditionally for SAS, there's a way to import data into CSV in SAS, but it's a long format. But in SPSS, in R, you can import it directly and you can export it in any format you want. Fine. All right. So unfortunately, I'll just give you a background information about the programming task, and then I'll attach appropriate link. So once you get access to this file, you just go to the link that I'm going to attach, and then you okay. So let me attach the link here. Where is it?
Okay.
Yeah. So here is the let me use this to bold it. Okay, so this one is the R codes for the multi-state. I'll just explain it briefly so that it will be you'll be able to work with it. Multi-state Markov model. Okay, and let me add R codes for classical survival analysis. Okay. And I think this is one example. And there are many. Just if you go to Google and type how to do survival analysis in R, it's just straightforward. Okay, so I've attached those here. So it means once you click, this will be clickable. When you get the HTML file, it will be clickable for you to visit that. And fine. So now let me just explain I just want to explain the research problem, and then I just want you to know how to collect survivor data. Suppose you are doing survivor analysis and you want to collect data from the hospital. Don't just go to the hospital and tell them that I need data on this to do survivor. They will not understand. They will actually give you a data, you can't work with it. So it means that you have to, most of the times, if you want to collect data from, let's say, clinicians, it's possible, maybe if possible, get a structure of the data in Excel so that they just fill it. They will just fill in those stats templates. That's the best thing, so that you get a data that is already in the analyzable format. Okay, fine. But there are instances where maybe the data you want is not in analyzable format. You should be able to transform the data and clean it and put it into the analyzable format, because you will not always get the data in the format you want. But this one is just to help you. If you want to do multi-state Markov modeling, how must the data be entered? That's what I want you to know. So this practice task, okay, is actually based on a certain disease called cardiac allograft vasculopathy. Vasculopathy. Okay, vasculopathy. To make life easier, I'll call it CAV disease. Okay, so we are saying the CAV disease is a progressive disease. So it means it's a disease that changes over time, and eventually it leads to heart failure. Okay, so by heart failure means that if your heart fails, you are likely to die. So it means eventually you could die. And it involves narrowing and blockage of the coronary artery in the transplanted heart due to chronic immune whatever. And now the whole point is that if we're to do the classical survival analysis, and I was looking at modeling the time to dying or the time to survival, okay, all I need is at the end of my study period, did an individual die or not? And if the individual died by the end of the study period, at what time did he or she die? And that's the time to death. Okay. And if by the end of the study, an individual had not died by the end of the study, then it means that the time to death for that individual will be the final time, and then it will be considered as censored data. Censored means that the individual is yet to experience the event. Even though we don't know the exact time the event will occur, we've attributed the final time as that. So we are just trying to say that the individual will die anytime after the final time. So it means to do survival analysis, your data must have censoring. At least there must be censoring. Censoring means that in real life, not all the individuals. So it means if you are doing a study, you want to do survival analysis, and all the patients you are using actually died, and you're looking at time to death. That data, since all of them had already died, none of them was censored. So it's, in that case, you can't use that data for survival analysis. At least you need some of your individuals to still be alive, okay, before you can apply these methods. These methods assume that not all the individuals actually experience the recurring event or experience that event of interest. In this case, the event of interest is death. And that is the classical or traditional survival analysis. But like I said earlier, that has limitation, because imagine situations where an individual came to the hospital healthy, and later that individual suffered from this infection, the CAV infection, and it was mild. And after some time, that individual had a severe infection. And at some point in time, that individual from severe just died. Severe means that the person is now close to heart failure, and then the person died. Or there are instances that when the individual got to the mild state, there are instances the individual could have recovered back. So it means this arrow you are seeing, you can add more arrows. So I could have had an arrow that is going back towards health. It means the individual became mild and later became healthy. But there's no way an individual can move from being healthy straight to severe. And that is what we mean by the Markov property. The Markov property is just trying to say that the current state of an individual, okay, is dependent on just the recent past, irrespective of the previous state. This is to say And before an individual would get to this state, severe state, the individual should have been mild. And I don't care about whether the individual was healthy. It means that severe status is wholly dependent on the mild state. The same thing, mild state is strictly dependent on the healthy state. And if there are instances where someone can have a mild infection and also get healthy, then there will be an arrow also going back towards healthy. And your model should be able to capture that. So here is just describing a situations where once an individual gets to the mild state, they cannot get back to healthy state. So in that case, it means someone can only move from healthy to mild, and someone can move from mild to severe. An example is HIV. There's no way you can get HIV and get back to healthy state. And maybe you got HIV, you are the mild state. The HIV has not developed to AIDS. And because of that, it looks like if you're not even sick. Then later on, maybe you are placed on ART, some therapy. And because of that, it looks like you are doing a bit better, but still you can never be healthy. You can never recover from the infection. You become healthy when you recover fully. So depending on some infections, the arrows will not go back to certain state. Okay, so that's all I want you to understand. And once you get to mild state, you either remain in the mild state or you go to severe. But we do believe that someone can be healthy and die. Someone can be at the mild state and automatically also die. Someone can be in the severe state and also die. But imagine situations where, so if you look at this paper where I use this for modeling a biological system. So this one, I was looking at survival, but considering a population of fish. Okay, so with this one, if you look at this curve, I mean this is called like a transition matrix. Here, I have 3 states. Situation where an individual, a fish is alive without the infection. 2 is a fish alive with infection, and 3 is the fish dead. And there was no way that a fish which is alive with infection, there was a way that a fish which is alive with infection could have recovered. But because of the study design, the way they designed the study, there was no way that happened. Okay, so that's why we are seeing 0 zeros at certain point. Anytime you see 0 here, it means that there's the transition from state 2 to state 1 is not possible, and so on. Fine. So this is basically what we mean by the transition graph, or the transition diagram. Fine. And so it means that for every disease, the diagram would differ. Let's say, imagine if it's HIV and we have grade 1, grade 2, grade 3, grade 4 before death. It means that if you do survival analysis and you are only looking at time to death and you ignore the various stages an individual goes through, your model is not realistic. That is why a certain famous statistician called George Box, if you go to any modeling class, that's one of the names you'll hear. George Box stated that all mathematical models are wrong, but some are useful. It's just to say that if all mathematical models were not wrong, even regression, then we will not have error 10. We are having error 10 because we don't think the prediction will be perfect. So it means that if you even fit a model which is too perfect that the error is almost 0, that is what we statisticians call it overfitting. We feel like it is too good to be true because we don't expect the model to be too accurate that way. So it means you can fit a model, it can be 80% accurate, it's good, at least it means it is 20% not accurate. But if you fit a model and it is 99%, 99.9%, that is a problem. That is why most of the times when we are doing hypothesis testing, we do it with 95 confidence level, because the truth is that you can never be 100% confident. And we only go for 99% confidence level when it depends on the nature of what you are studying. If you want to prioritize accuracy over anything, then in that case, we go for 99% confidence. Fine. So this is the nature of the data. So imagine a data where an individual could be healthy and later get mild infection. From mild infection, the individual can progress to severe before they die, or at any point in time, the individual, at any stage, the individual can also die. And if it was a disease where from mild you can go back to healthy, imagine if it is malaria, then from mild you can go back to healthy. And in that case, there will be an arrow towards that. Fine. So the data you are going to use is actually an inbuilt data in R. It's called the CAV data. And it is one perfect example for multi-state modeling. It helps you to know how the structure should look like. So the data we are going to use has these variables. So the first variable is just patient ID. And remember that to do multi-state modeling, your data must be what? Your data must be longitudinal. As a matter of fact, even for cross-sectional data, even for the standard survivor data set, every survivor data is longitudinal because you are looking at time to what? Time to a certain event occurred. So it means patients started at time 0 and you are tracking their progress over time. So that's why almost every survivor data analysis requires a longitudinal data set. You can convert the data for a multi-state back to the classical survivor data set. And that's what I did in this code below. I demonstrated how if you wanted to do the standard survivor, just looking at predicting the time to death, then in that case, you need to restructure the data in a certain way. And if you want to do the multi-state, then the data needs to be restructured in a certain way. So now the data we have here is in a multi-state fashion. So if you look at this patient, so this is how the data looks like. So we have a variable called PT norm as patient ID, and their age, the age of the patient at the time of the heart transplant in years. And we also have something called a variable called years, and that years, this variable called years, it is actually the time since transplant for the recorded patient. So this is actually that survival outcome. So it's just like saying the time. So this is like the time since the transplant. Okay. So one could say, one could call this as, if I want to define it very well, I could say time to heart transplant. Okay. So because I told you for survival, we always, the outcome should be defined like time to an event, time to event. So time to, what is the event? In this case, the event is transplant. Just that we are saying that once an individual has that transplant, they can undergo any of these states. The individual could be healthy, and later on, the individual could start getting mild infection, and then later it can be severe, and at any state, they can also die. Fine. And so we have the time to transplant, and then we have age of the patient at that time. As at the time the patient got the transplant, what was their age? And we have a variable on sex, and then we have primary diagnosis that led to the heart transplant. Okay, and then we have cumulative number of acute rejection episodes for fine, and then we have, this is the multi-state. This is the state that is defining the health state, whether the individual is healthy at a particular time, whether over time the individual changed to a mild status and then maybe progress from mild to severe. This is where you track that history. And then there's a variable called first observed. This is just indicating whether the records corresponds to the first the patient first observation. This is to say it helps us to track this first observed. So for instance, if you look at patient, the first patient with ID ending at 2, so you notice that it was 1 at the beginning and 0 everywhere. So now I've extracted that patient. So for that patient, you notice that for the first observed variable, it is 1 at the beginning and 0 everywhere. This is to say the patient entered the study at this particular time. It helps us to know at what point in time the patient first entered the study. Okay, so that's what that variable is tracking. And then this state max is a variable that helps us to conclude on censoring. Okay, there's a variable that helps us to conclude on censoring. So now let's look at the definition. So for instance, this state one means healthy, 2 means mild, 3 means severe, and 4 means dead. And then now let's look at this state variable and the state max. Okay, now when the state is 1 and then the state max is 1, it means that individual is healthy, and that individual is healthy, and they've not they've not experienced any other event. At this instant, that individual is healthy, and then they are still healthy. Fine. So situations where now here the state is okay. So for here, always for this particular ID, all the states coincided with the state max. Now let's look at situations where it didn't, and let's look at how we can define. So now I want to add 2 variables which are not in this data. So I want to add censoring status. And I also want to add survivor status, whether dead or alive. You notice that for the state, if we are in state 1, 2, or 3, you are alive. And then if we are in state 4, you are dead, right? So I want to add that as a variable to the data, such that for the censoring status, if you see 1, it indicates that the patient experienced the event before reaching an absorbing state. An absorbing state is dead state, okay? And then 0 means that the patient was censored. Censored means that they remain in that state, or they are yet to, censoring means they are yet to experience that absorbing state, that death, the death state. They are yet to experience that. And if someone is alive and they are yet to experience the death state, okay, if someone is alive and they are yet to experience the death state, okay, it means that patient is what? They are yet to experience the death state and the study is not over. That patient is not censored. Censoring only occurs if at the end of the study, that patient is yet to die, then that patient is censored. Fine. All right. So here, all I'm trying to say is that in order to add a censoring status, situations where the state variable and the state map variable are not the same, we are saying that that individual is censored. And situations where they are the same, that individual is not censored. And for the death state, like I already said, once any state is not equal to 4, once we have state 1 is not 4, state 2 is not 4, state 3 is not 4. State 1 is they are still healthy, and 2 is they are mild in infection, and 3 is they're severe. Any of these, you are still alive. So here I'm just trying to say that once an individual is in any other state, which is not the maximum state 4, then that individual is what? Is alive. And then the individual is dead. 1 means dead if they've reached the maximum, and if not, then they are alive. Fine. So so it means that this is the key. 0 means alive, 1 means dead. And with this one, 0 rather means censored, 1 means that they've already experienced the event. Fine. So that's just how the data. So I've added the functions I've created here. It is not on this website. Okay. So it means for the website, you are not going to look at how they extracted their data. You don't need that one. You also do, all you need is from this part where they are talking about how to use the MSM package. So there's a package called MSM for multi-state modeling. So starting from here, then you can start using the package. Remember that they are doing the analysis assuming these possible transitions, but you could decide to assume that someone can move from mild to healthy if that existed. Okay, fine. So it means that transitions would always be dependent on what you are doing. For my study here, once an individual is dead or alive, is alive, okay, without the infection, they can either be alive with the infection, so they can either move from state 1 to 2, but they can't move from, how do you call it? They can't move from states. What was the point here? Okay, state 1 is once an individual is alive without the infection. Over time, they can have the infection or they will die. But in the data, the way the study was designed, all the fish were not in the same, let me say, environment. We studied each fish in isolation. So it means that it was such that once a fish is infected, okay, if an fish is infected, the next state is they can die or they can lose their infection. Okay, or they can lose their infection. So that was that. So it means that was the possible transitions. Either you are dead, either you are alive without the infection, and later you get the infection, and from there you die. But if you are dead, you cannot get reinfected. And then so it means that always to define the possible transitions, it is always dependent on what the disease is and what characterizes the data you are working with. And a take-home message is that possible transitions are described based on something called a transition probability matrix. And that is like what I was trying to define. I was trying to define here, okay, in that sense, fine. So in this case, so it means that just follow these codes This code is just trying to tell the number of transitions that occur between state 1 to any other state, and then it's looking at how to set up the model and so on and so forth. Yeah, so that's one thing. And the beauty about the structural, the multi-state Markov modeling. So the paper that I was telling you about, this is the code that was used for that, but it's quite long, so I didn't want to. The beauty about this is that the predictors that will predict transition from, let's say, healthy state to mild state might be different from predictors that will predict transition from mild state to severe state. So it means it can investigate much more complex directions. So it's just, that's the beauty about the multi-state, that you are also able to check predictors that influence some specific transitions. So there are more you can do to it, and the mean time to remain in a particular state. And so if you get access to this particular paper, it will help you, that paper, it will help you to know the other things you can estimate from it. Yeah, so estimating probability of transitions and so on. So, and giving some covariates and so on. So yeah, so basically extracting the data, I've done everything for you. You only need to use this this code and go through the modeling part. So for instance, the variables I've added, they didn't add it to it. So I created my own function to do that. The dead state and the sensor state, I've created it to do that. And here I'm able to check all the patients who were censored, okay, or who experienced censoring. And yeah. And for the censoring status, here, now let's look at why the censoring status is 0. 0 means that the patient is not censored, right? So this one, anytime the state matches the state max, it means it is what? If it matches the state max, okay, then it means the data is not censored, right? But situations where here the state was 2, right? And then the next one, the next one was rather 3. It didn't match it. Then the censoring status is 1. What this means is that this patient, okay, who is in the mild state, we didn't know the exact time they remain mild at that point in time. So it meant that patient, so in that case, the possible transition they could get is what we mean by the state max here. So this is to say, if they don't agree, then we are saying that they are censored, right? And so that's basically how they were trying to use. But if I was the one entering this data, I won't define a variable called state max. I should be able to check whether that individual was censored or not. I should just create a variable. If they've not died, it means they are not censored. And then by the end of the study, if they are dead, then it means they experienced the event. If they are still alive by the time the study ended for them, then it means they are censored. Fine. So that's how I would have done that. Okay. So here, so I started. So I think I first started. So what I did here was I created a function to extract the last row of each of the patient data. But the last row means that I'm now looking at the time to just death. So the time to just death means that for each individual, I notice it's longitudinal. So I'm looking at the last data for each individual. If we extract the last data for each individual, it is equivalent to the data you use for the normal classical survival analysis. Okay. But if you are now using their entire history, what all the possible transition they experience over time, then that is the second phase, which is the multi-state. Okay, fine. So I just started going through that, but time couldn't permit. So this is an example of the Kaplan-Meier curve. So here we are looking at comparing time to death between males and females. Okay, and this p-value is the log rank test results. So that tells that there was no significant, anytime the curves between males and females, there's any intersection, then the log rank test will not be significant. But for us to see a significant difference in their survival, we don't expect the two curves to intersect at any point in time. Okay, so without wasting time, I will end here. There are a lot you could have done with it. And I think there's already a YouTube channel, a YouTube video on this survival analysis. in depth and what the kind of testing you should do. I think if you look at even this video, survival analysis, the part D and the multi-state, I think I even introduced that a bit there. So you can take a look there and that's fine. So please make use of this data. So here I've done the data already. I've extracted and added variables you need to add and everything. All you need to do is to go through the multi-state codes and go through the survival code to see how we do the standard survival analysis and so on. Okay. All right. So without wasting time, I'll end here. I can take a few questions. And thank you.
Hello. President, please, can I speak?
Yes, please.
Okay, this is Bernard. No, honestly, you've really done everything. You've touched on. Happy. I don't know what to say. I just want to know when are they going to even give you a professor from Oxford?
Mercy.
Please. Yes. It should come as soon as we will come and give it to you. Okay. So no, thank you for the how are we going to not to bother you but to contact you or send you a mail touch from time to time? You made mention of a pizza.com. We said we should send you a link to enroll you or something. So we want to know.
Yeah, so I think at the beginning of at the beginning of my presentation, I said, okay, it's fine. Let me just put it on the chat. But if you go to Google and you type my name, Clement Chumesi, you see the first, how do you call it? This one, my Oxford University website. If you click on that, you get access to, even my number is there, but please don't call. You can text me a WhatsApp message, but that's fine. But
I've already sent you a WhatsApp message.
That's fine. But my email address are there. So that's my Oxford University email address and that. So if you want me to add it to the Piazza so that you can have access to the course and everything,
yes,
you can just send me the email. But for those who are part of the NUGS-CHINA guys, all I'll do is that I'll send the HTML file and everything to your president. Is it Ben? I'll send it to him, and so that you don't have to go through that stress of that. But the truth is, if you want to get access to all the course on my YouTube channel, then you really need to enroll on the Piazza. So for the Piazza, once you send me, just send me an email and indicate that you want me to add you to the Piazza platform or to enroll. I can't add you directly. You have to enroll yourself. But how to enroll is that I would. So for instance, on Piazza, if I go to where is it? Okay. Just a minute. Okay, this resources. Okay, so if I take away this one, okay, login. Okay, so on Piazza, when I go to manage class, I will just send you. So once I put your email here, it will enroll you. So this one tells you that about 340 people are already enrolled. Okay. So once I put your email and click add, it will send you an automatic email. And that automatic email, that automatic email, there's a code that you will need, but that code in the automatic email is not correct. So what I do is that whenever I send you that automatic email, I send you a second email with specific details to follow. Okay, so you look at that specific details and then you come, but the link to enroll it will be in the automatic email, but you need something called access code. And the access code is this one. This is the access code. But in the automatic email, I think the access code is wrongly defined. People were complaining that it's wrongly defined. So I send them the correct one and then specific information in another email so that you know exactly what to do. Yeah. So that's the best. I think, yeah. So that's it.
Okay. Thank you. Thank you.
No worries.
Yeah,
Okay.
Doc, thank you. I just wanted to find out with regards to the functional data analysis, where you convert your data into curves.
Yeah.
Could that one be used as a form of finding whether your data has a normal distribution or otherwise?
No, not at all. So for the functional data analysis, so first of all, remember that all the statistical tests we know, ANOVA, regression, principal component, we have its functional component or its functional form. It means that all the classical statistics we do, the functional data analysis has a one-on-one mapping of each of those methods in the functional form. Okay, so it means if we want to test for normality, we have a statistical a normality test in a functional form for that. But the beauty about functional data analysis is that it is often used when you want to identify patterns in the data, especially when the data has noise. So with the functional analysis, after converting it to curves, there's some smoothing function that we can apply, such as B-splines, that can take away or denoise the curves or the data so that you'll be able to see the patterns clearly. And remember that the data must be in a longitudinal fashion before you can apply that. And it's applied to different areas of application, engineering, in medicine, and all those things. It's applied there. Think about it. Survival curves is just like a unique example of a functional curve. Just that with the survival curves, you cannot integrate or differentiate the curve. But with this functional data analysis, all the data we are working with are in the real space. It converts the data from the real space to the Hilbert space. Hilbert space means that the data are in curves that are differentiable, so that if you want to even investigate the rate of change, you can take the first differential. And the first differential, it will be the rate of change. So in that case, you'll be able to now plot or visualize the rate of change in your outcome over time. So time will be the x-axis. And then that variable that has been converted, the outcome that has been converted in functional form will be the y-axis. And you can even find the second derivative if the second derivative has a meaning. I mean, in especially if your data is about distance, then it means that the first derivative would literally be what? Velocity. The second derivative would be acceleration. And if it is something else, it can have different meanings. But always the first derivative is the rate of change. Sorry. I hope I've answered your question.
Yeah, that's very good.
Okay, can I take one or two more questions and let's end.
Yeah, Doc, I have a question, but just that I can't find a place to raise my hand.
Oh, just talk.
Yeah, so I wanted you to really explain the factor analysis and the PCA again for me. In summary, do you mean I cannot do any factor analysis using numerical data?
So basically, yes. So basically, factor analysis and then principal component analysis, I want to say they are similar. Similar doesn't mean the same. When something is synonymous, it means they are almost the same, but not the same. It's just to say that for factor analysis and then principal component is applied to only numeric data. So it means that if you have a categorical variable that you wanted to even include in the principal component, that categorical variable has to be included as a numeric variable. By numeric means that I don't have to assign labels. If it was male was 1 and females was 2, I should maintain it just like that. But if all the variables are categorical, especially those who do a lot of questionnaire or Likert scale kind of analysis, okay, especially those who do you have some scales that there are something called latent variables. So latent variables are those variables that you cannot observe from based on. So for instance, if I ask you your age, I know there's that age. So for instance, if I want to know your academic performance, I can use your GPA or something as a metric. But if I want to know your happiness and I want to quantify your happiness score, there's just no way. But they are latent. There are some standard questionnaires to quantify all those social variables, your post-traumatic stress, your satisfaction, and all those, especially those who are into psychology. They do this kind of latent variables analysis a lot, because most of the variables they work with are latent. They cannot quantify it from an observed variable. They cannot observe it, but they can use some indicators or some construct to help quantify those latent variables. And so basically it means that in order to do factor analysis, first of all, the variables must be categorical. That's for factor analysis. But for how do you call it, principal component analysis, the variables must be numeric. The variables must be numeric. But one thing I have to advise is that factor analysis has two types. So we have the confirmatory factor analysis and we have the exploratory factor analysis. Okay. So for the confirmatory factor analysis, structural equation modeling combines the confirmatory factor analysis and path analysis together. So the path analysis are just set of regressions. As you can see, with the structural equation model, there are set of regressions you are interested in, and you want to investigate them at the same time. And that structure, okay, you want to confirm that structure. That is what we mean by confirmatory factor analysis. You want to confirm that structure you've hypothesized. But I was saying that if you don't even know the kind of structure, then you can couple hierarchical stepwise regression with moderation mediation analysis in order to get a potential idea or a fair idea about the kind of structure your SEM should look like. And then you can now confirm with structural equation model if that is the case. Fine. So in summary, for factor analysis, especially if you are interested in using it for dimension reduction or reducing the dimension of the data, especially if you have a scale to quantify a latent variable, and you believe that not all the variables are important, and you want to know which subsets are more important and the ones you should take out, is going to employ some principle of principal component. But if the data is categorical, that principle is based on factor analysis. And if they are all numeric, then it's based on principal component. But remember, never include the dependent variable as part of PCA or factor analysis, especially if you're reducing the dimension of the data. Okay, all right. And those who do like proteomics and genomics, they do PCA a lot.
Thank you, Doc. And so in that case, how is the factor analysis different from logistic regression?
Oh, logistic, you see, like I said, for factor analysis, we are just reducing the dimension of the data, just like principal component is doing. But logistic regression is when you are looking at factors predicting some categorical outcome. So it means factor analysis is not a regression. PCA is not a regression. It's not a regression. Logistic regression is a regression model where the dependent variable is categorical. If the dependent variable is discrete, then it's Poisson class of models. An example of the Poisson class of models is Poisson regression, quasi-Poisson, and negative binomial regression. And situations where the dependent variable is continuous, then we have OLS class of regression, generalized least squares, and or even ANCOVA. Unfortunately, I didn't talk about ANCOVA. You see, the difference between ANOVA and ANCOVA, you see, ANOVA is like you are comparing some continuous outcome between three or more groups, right? But imagine where you have a situation where you have a data you collected at baseline at time 0, and then you collected that data at a future time point, and then you wanted to look at comparing the difference in looking at how the feature or the post baseline data differs between your treatment groups or some categorical variables, and adjust for the baseline variable. In that case, that is what we mean by ANCOVA. And remember, it's not just baseline. Think about it as any instance where you have a certain variable that is not a predictor, but it co-varies with the outcome. This is to say, once the outcome changes automatically, that also changes. Then you can add that variable that co-varies with the dependent variable in any regression model. And the moment you do that, example is the baseline scores. If you add a baseline score to any regression that you've been doing, that regression model is called ANCOVA model. So ANCOVA is just like adding any variable that co-varies with the outcome. It doesn't necessarily have to be baseline scores. It could be instances where it could be, let's say, you have immune response, and then you have a certain variable that automatically, once it increases, immune response will also increase. So it means that it's highly correlated with the outcome. You can add, because remember we said for regression, we expect the predictors to have high correlation with the outcome. So it means that even if other predictors are not highly correlated with the outcome, but you are able to identify a certain variable that co-varies. By co-varying means they are highly correlated with the outcome, then what that means is that it's going to help improve the model because of the high correlation just that variable has on the outcome. So that's basically, in that case, you are using that in a way to improve the strength of associations of the other predictors on the outcome. So that's what we mean by ANCOVA. And with ANCOVA, you can also include interaction effect in the model. Yeah, so basically that, but you can do ANCOVA without interaction. So all the regression model you've been doing, the moment you add the baseline scores and you are predicting some future time scores of some outcome, that is an ANCOVA. You can include interaction effect, and it's still an ANCOVA. Have I answered you? Usually, I answered your question more than you need, so that
You've done well.
Okay. Okay, so I think we should probably end here because of time.
Yes. So, Doc, we thank you very much. I think the president can speak now.
Thank you very much, Doc, for the question. Unfortunately, Bernard, we cannot allow you to continue because we are going to end it here.
Okay, thank you.
3.5 hours into the training, and Doc is tired. We need to let him go. So perhaps you have his details, and you can send him your request and all other questions personally via mail or via chat. So
okay.
All right. On this note, I would say a very big thank you to you, Dr. Clement Chumesi, for your time with us and for your insightful presentation. We have learned a lot within this short 3.5 hours. I think you've taught us from grade 1 statistics to very advanced statistics. And we are very, very, very grateful for that. So Doc, on behalf of the HICF leaders, I would say a very big thank you. On behalf of NUGS, I would say a very, very big thank you. And there's a proverb in our language that if the housefly has nothing at all, at least it has its hands to rub each other. So I would call on the Vice President of NEC to present something little that we have put together to appreciate your time and the efforts that you have put into this. Vice President, Your Excellency, you have the floor.
Hello, sir. Please, is my president here? Madam President, are you here? Madam President? Madam President is in, but
Honorable Ben, I'm here.
All right. Please, Madam President, do us the honor.
Thank you very much, Honorable, for giving me the platform. And Dr. Clement, I want to say a very big thank you before reading our citation. God bless you for taking time, 3-4 hours out of your time to break this whole our software down to our level. God bless you. I want to take the opportunity to read our citation. The entire membership of the National Union of Ghana Students, NUGS-CHINA, would like to express our sincere appreciation to Dr. Clement Chumesi in recognition of your outstanding contribution as a distinguished speaker on our statistical software on December 7th, 2024. Your insightful knowledge, expertise, and engaging presentation have not only broadened our understanding of statistical tools, but have also inspired us to explore the power of R in research, data analysis, and academic pursuits. Your dedication to empowering students with practical skills and your commitment to academic excellence reflects your exemplary leadership and passion for education. We deeply appreciate your willingness to share your time, experience, and wisdom with our union. Your impact on this event will resonate beyond today, fostering a stronger academic foundation for Ghanaian students across China. With profound gratitude, we honor you and your invaluable contribution to the success of this program. God bless you, and a very good evening to you. Thank you.
Thank you very much. Thank you very much. So please, I will entreat you to encourage others to subscribe to the YouTube channel and learn at their own pace. I don't get anything from it at this stage, but I think for me, I'm just more interested in always making that little difference. And the lives I touch, to me, is more rewarding than even money or than anything. And I encourage most of you to also do the same when you develop if you have any expertise that you think others could benefit from it. I think in that way, it might look like you're not getting much from it, but the truth is that people are watching from afar. So I also thank you for the opportunity. It's been like over 5 years or so that I've been doing this every year, and I'm always happy to help. Yeah. So thank you very much, and I'll be happy to get the citation sent to me privately.
Sure. It would be sent to your email after the training, and we will share your social media platforms, that which would need to be subscribed to our members to do the needful. Yeah.
Okay. All right. Thank you. And I'll be happy to get the recording so I can put it on the YouTube channel. And I'll try and split it and take away things that are not important, and so that it will just be focused on the status car bit and people can just watch it in a better way. Yeah. So thank you very much.
You're welcome, sir.
Thank you. Mr. Johnson.
All right. Yeah. Bye-bye.
All right. So thank you very much, Doctor, once again. We know that no amount of whatever we have can actually replace what you have done for us, but we are grateful for supporting our research with your insightful presentation. So on this note, I would bring the meeting to an end. And like we said, this Skill Up is a process. We'll be having some other courses coming up next week. So next Saturday, we'll be looking at how students can write articles in LaTeX. So there are several other courses coming, data analysis with Python, data analysis with other softwares coming up. So we hope that the numbers that turn out today would do so in the subsequent training as well. And Doc, in case, going forward, we find some topic that we believe you can give a very extensive talk on. I hope you wouldn't mind if we reach out to you once again.
Oh, no problem. I mean, so for instance, all the publications I showed you guys were all written in LaTeX.
Okay.
So I use LaTeX for everything I do. Okay, no worries.
I understand, but we have a speaker for LaTeX, so I'm just saying in the near future
I'm fine. I want to be a speaker for LaTeX.
Exactly.
But if it's about maybe empowerment, if it's about future career, like how to that kind of thing, anything, anything academic, that's fine by me.
Most definitely. Thank you so much, Doc, once again for your time. And thank you all members of NUGS and HICF that made it this evening. We hope that we can hear from you and see you sometime next week. So on this note, we adjourn the meeting to next week. Have a wonderful weekend and an evening as well. Thank you all for coming.
Okay,
Thank you, Doc.
thank you.
Bye.